morning, dear colleagues. Welcome to the Department of Archaeology of Lithuanian Institute of History in Vilnius. It is great to see you all online for this conference. And I wish to express my deepest gratitude to all speakers and all the listeners. And I also want to thank our IT support staff member, Karolis Gerižinis, who will screen the conference and help us in the event of any technical issues. So thank you very much, Karolis. Before we start with the first part of the conference, I want to announce some minor changes to the program. Giovanni Freni will now be speaking at 10:20 a.m. after switching with Mirjana Radivojevic, who will be speaking at 12:40 p.m. Giovanna, thank you very much for being flexible with your time to enable us to hear from as many guest speakers as possible. It is a pleasure for me to start our conference with the presentation, Why Should We Investigate Heavy Metals and Toxicity in Prehistory, Aims and Challenges? And I will share the presentation. You can see and hear me, yes? Dear colleagues, yes. Okay. So it's an honor to speak for me to start our conference with this presentation, Why Should We Investigate Heavy Metals and Toxicity in Prehistory, Aims and Challenges? And I will start by answering an important question, namely, why this topic? And heavy metal pollution, exposure, and toxicity in prehistory is a new and uninvestigated topic. Preliminary environmental and anthropological research yielded strong evidence of heavy metal pollution and exposure increasing with metallurgical activities. There are many archaeological sites with a huge potential material for investigating heavy metal impact on the environment and human health. New scientific methods enable us to analyze environmental and human health conditions, as well as gain new insights into the social lives of individuals in prehistoric communities. Investigation of heavy metals and their impact is an idea which first focuses on both the interplay between nature and humans and promotes interdisciplinarity. Heavy metals are dense metals with a high atomic number and atomic weight with a specific gravity greater than 5, and most are usually toxic even at low doses. Typical heavy metals refer to cadmium, lead, mercury, and chromium. However, iron, copper, aluminium, zinc, beryllium, cobalt, manganese, and metalloid arsenic may also be deemed as heavy metals dependent on the context. Human bodies have small amounts of metals like copper, iron, and zinc, which are important to keep our organs functioning. If there are too much metal accumulated within the body, it can damage vital organs like brain and liver and have an adverse impact to bones. We see here on slides heavy metals which are most hazardous, and it's listed here. You can see these elements, but I will not go here most in the details because we will hear about this today in a presentation of our colleagues toxicologists, Linas Zdanavičius and Robert Kasbadaras. Heavy metals fight with components in the cells like enzymes and proteins, which are important to help the organs function. If the organs are not able to do their job, because we are getting bullied by heavy metals, humans experience symptoms of heavy metal poisoning that can be life-threatening without treatment. We see here on slides the arsenic impact to human health. When talking about heavy and toxic metals in the archaeological record, we have to keep in mind that contamination can be natural or anthropogenic. The latter caused by activities like fire making, mining, smelting, and other paleo-industrial technologies for the processing of raw materials. There are at least 4 areas of pollution which must be addressed when dealing with the anthropogenic input of heavy metals into the environment. Atmospheric contamination, soil contamination, water contamination, and also human-made artifacts. Prehistoric metallurgy is usually understood and described in terms of consequential innovations and technological progresses with the emergence of strongly built elite groups and pyramid-formed social structures. However, the discovery and progressive exploitation of copper and other metals resulted in the release of metals to the environment, in the atmosphere, water, and soils, which entered the food chain and prompt us to reconsider the role of metallurgy in human history. We see the studies of our Spanish colleagues with the picture of pollution, air pollution in the places close to metal mining regions. Shortly after the learning how to cast copper, a new melting method was created. We will hear about it more in the presentation of Paolo Picardo. The said method entailed the large-scale emissions of vapors. The metallurgical cycle is very complex and involves complex human behavioral actions from the starting point of productional chain to the final deposition of metal artifacts. Every stage of this cycle impacts the environment and human life, be it directly, like miners and craftsmen who come into unmediated contact with copper, or indirectly, like consumers who receive and utilize the products. In terms of toxicity, the greatest exposure to copper certainly occurs during smelting, particularly during bronze production. Mercury and arsenic are released during the smelting of thalor, but also other elements such as lead and antimony to lesser extent. During further processing, like casting and forging, the toxic load is certainly a little lower, since not as many heavy metals are released, but is still present in a considerable amount. It is clear that prehistoric metallurgy and its consequences must be analyzed from this perspective within a systematic and interdisciplinary studies, which will not only change our understanding about metallurgy, but also promote a mutual beneficial partnership between different spheres of academia. So the aims of such studies are as follows: to evaluate the level of heavy metal contamination caused by prehistoric metallurgical activities in the natural environment and in the human food chain, archaeological material, paleobotany, pottery used for food, and human bones in different European copper ore mining regions during the Copper and Bronze Ages on the macro and micro levels. To identify and compare the physical pathologies affected by heavy metal exposure in human bodies that first reside in nearby mining regions, copper suppliers, and second, produce and use metal artifacts, craftsmen and consumers. To identify whether the oral microbiome of societies involved in mining and smelting activities is enriched with heavy metal resistant microbes and genes, which may then be interpreted as having a higher tolerance to heavy metal toxicity. To undertake a comparative analysis of the results obtained from the temporal perspective and to elucidate the dynamic mechanism of metallurgy and the social status of metallurgists in copper and Bronze Age societies. To develop a holistic research framework that clarifies the negative impact of prehistoric metallurgy through analyzing the intensity of metal pollution in the environment, in the atmosphere, water, and soil, and determining heavy metal ratios in the food chain through examining animal and fish bones, human bones, and plants. There are plenty of places in Europe, such as Ebuna, we see on slide, where ore can be actively exploited starting in the 4th millennia BC. We see the amounts of metal exploited in Ebuna on the slide. We selected 60 sites of the Copper and Bronze ages, covering the time period from the initial phase of metallurgy in the second half of the 4th millennium BC until the outset of the Bronze Age in around 800 BC in the Alpine and Carpathian copper ore regions, the most important copper sources during this era. The selection is based on their close vicinity to prehistoric copper mines and smelting sites, as the highest heavy metal pollution can be expected in the immediate surrounding of these places. Settlements with evidence of intense metal production and burials with metallurgical equipment belong to this group too, and we will hear today several presentations about these exceptional and very important sites. In order to ascertain a full picture of metal technology, all the available evidence from ore sources to finished objects can be analyzed. The selected sites also form part of a rich hoarding landscape. Metals are found as hoards in the settlements or beyond. Wherefore, it is possible to compare the data with the large body of archaeological, geological, and archaeometallurgical analysis in the long-term perspective. It is important to reflect on the many harmful substances people used during the mass production of metal, what kind of vapors or fumes they inhaled, and how dangerous it was for their health. This knowledge is essential for several reasons. First, further exploration of the toxicity of metals may lead us to reconsider the living circumstances of human beings in the past. The detection of the ratio of heavy metal pollution in the paleoarchives and in the surrounding areas of the living spaces enabled to realize these tasks. And we will hear today a wonderful presentation of our colleague Daniel Beres about paleoenvironmental pollution. Also, palynological and geochemical analysis of peat have the potential to yield profound knowledge about the impact of past mining activities on the environment and are valuable for explaining human-environment interactions in the mining landscape. Furthermore, palynological analysis indicate clear human interference in the natural vegetation, such as forest clearing. and changing in the land use, where values of anthropogenic pollen indicators increased synchronously with rising heavy metal ratios. And the microbiomes of soils across archaeological contexts give us further information about whether the effects of metallurgical activities are visible in the environmental microbial communities. And studying soil microbial communities is important because they play key ecological roles that are vital for the sustainability of life on the planet, such as cycling carbon and plant growth. It has been shown that the recovery of ADNE from deposit sediments has provided novel insights about past climates. Second, as archaeologists, we can examine human behavior, such as overlooking pollution and disregarding the detriments of advanced living over a protracted period, because they found the advantages whereof too alluring. And third, populations may have developed natural adaptive capacities to cope with the toxicity of metal. To summarize, there are questions which can be clarified in the future studies, namely, what was the level of heavy metal pollution and food contamination in these areas around the important European Copper and Bronze Age ore sources and mining sites? What different health conditions can be observed from the mining societies, copper suppliers, and producers of metal artifacts? What physical and social differences can we trace within one cemetery with regard to health conditions, gender, and age? How can the pollution and toxicity contribute to a novel understanding of resilience and sustainability in Copper and Bronze Age societies? This has only recently become possible due to the ability to analyze chemical and microscopic traces in human dental calculus and detect combustion markers, and within dental calculus, analyzing the ADNA and microbiomes in dental calculus with the application of high throughput sequences technologies to dental calculus and bioinformatic workflows, using lipid biomarkers and pollen-based reconstruction of temperature to analyze how climate change events and human impact have shaped the environment, and the possibility to measure heavy metal ratios and detect isotopes and ADNE in cremated human bones, and of course all other important methods as well. So why is this idea so important and innovative? Because working on this idea, we are able to undertake cutting-edge research to produce and integrate comprehensive bioenvironmental, anthropological, genetic, isotopic, chemical, and medical analysis of the material from resettlements and burial grounds around the Alpine and Carpathian copper ore deposits from the late 4th millennium BC to the end of the Bronze Age. Produced the first results ever on the study of oral microbiome in societies involved with mining and smelting activities to explain heavy metal resistant microbes and genes. We hope to position ourselves to be able to compare two control groups for the purposes of studying their health conditions and gauging their levels of immunity to heavy metals. Reveal more complete picture of how metal workers operated and interacted within the boundaries of their personal, social, and environmental surroundings. Establish an innovative multidisciplinary approach to the study of prehistoric metallurgy and provide a framework for assessing past human activities and their environmental impacts. to interlink genes and microbiomes as factors for shaping patterns of communities' life expectancies and demographic fluctuations in the active metallurgical zones, and to shed light on the social structure of prehistoric metallurgists and better understand their living and working conditions, as well as their tolerance levels to environmental pollution. And finally, to unravel the deep history of complex metallurgical activities and help to understand present-day health and environmental challenges. Thank you very much for your attention. So can you hear me, colleagues? Yes?
Yes, sound loud and clear.
Yeah.
Yes.
As we are out of schedule because my technical issues, I would like to invite now Paolo Picardo to present talk about copper-based early alloys, voluntary or fortunate event. We are very looking to hear. Welcome, Paolo.
Thank you. So I will try my best to share my screen and waiting for this moment. I think it is a real honor for me to participate in this conference. So thank you, Agne, for the work job you made. I think that it is very, very, very interesting what you are proposing, and I hope that I will be able to be of interest for you too. So can you see my screen? Yes, I think so, right?
Yes, we can.
Okay, perfect.
Yes.
Well, the introduction, I mean, the first conference, it's probably much more interesting than mine and has a very wide point of view. And but I will do the best to keep your interest on the practical aspect of alloys. And I am already asked your indulgence if I will say something you know better than I do, but I'm a simple and humble metallurgist and chemist, so I just try to give my contribution at the best. And before to start the presentation, I'd like to say that in my region, in Liguria, I've seen there are 2 stars in the map presented in the previous speech, but there are many more mines that might be investigated and studied. And being a part of a team working on those mines, I offer our full cooperation to have samples and to study. And for example, we have a microbiology team working on mushrooms growing on the soil of these mines, where the concentration of metals is important and can be used as detector for pollution and for the presence of metals. So this is just as a comment to the previous conference. And copper-based early alloys. So we know that copper is something very important, and we know about early alloys thanks to archaeological findings, ancient mines, material properties, assumptions, and also mythology. So I have looked around for a nice picture of Hephaestus, and that's one of the best I found. So I just to point the fact that there are gods of metals, and we know that metallurgists had an important role in the society. Also in Sumerian society, they had a very important role, and they were considered to be like rich slaves, because they were rich due to their knowledge and skills, but they couldn't exit from the area of the king because of the preciousness of their skills. But if we go more deep in time, we have always the information that starting from a certain moment, alloyed copper objects have been found. And each time I talk to an archaeologist, mainly on those working on the eastern part of Europe, they tell me about a more ancient finding, which is putting back in time the beginning of metallurgy, not only related to finding native metals, but also to production of metals. But at the same time, by our experience, we know that the moment we find an object with, I don't know, for example, 5-6% of tin or arsenic or antimony, it means that there has been at least 2 centuries behind of experience. So it's not just the earliest period, but it's the testimony of something which has been already developed in the past centuries. However, we are missing a lot of information, and the president's speech was extremely interesting for me because it was the same thing I thought about crossing disciplines to have a better vision. But let's talk about metals. We all know that among the first metals used by humankind, we have gold, which is important for its preciousness, but less important for practical activities, and we have copper. And copper in the mines can be found on top of the mines in forms very colorful, like a native copper related to other colored compounds, like we have examples here of malachite, of azurite, and chrysocolla, and so on. But we can consider that if today finding this kind of examples, it's more and more rare. This is not the case in ancient time, where no mining exploitation were performed, and then it could be possible to cross these kind of colorful veins of metals in the correct areas. And I live in a region where this is quite common, so we can still find some areas where it's possible to find this kind of minerals and native metals. But at the beginning, so it was probably a question of observation. Then the native metal was attractive, and at the level of pollutant, this native metal has nothing. There's no problems, because it's just a metal which can be deformed to obtain the final shape, can be melt and then cast to even better match the desire of the artisan, but they do not really create great vapors or dangerous fumes. The problem starts when there is this understanding that if I have, like in the picture you see here, if I have copper connected, strongly connected with this greenish area, then maybe I can extract copper from this greenish area too. And if I break this partially stone, I can observe inside that there are these colored areas. Of course, there is this kind of intelligence, instinctive intelligence, that creates the idea that maybe we can extract, or we can use these colors on other activities like decoration of pottery and so on. And using a specific reducing atmosphere, then we can extract copper. Once we do this, then we enter in the next step, the step of production of metals, and then we start to enter into the pollution process. I remember a study performed in the 90s where there was carottage at the Antarctic, so the South Pole, to see the quality of the ice and to see also the pollution of ancient atmospheres due to various natural and anthropic effects. And they found the beginning of the extraction of metals, melting of metals, with an increase of heavy metal in the ice level. So this was meaningful, and I think this is all really meaningful with the topic of this conference. But why didn't we stop with copper, and why did we looked for alloys? Well, the reason is a simple mechanical and practical reason. Copper is soft and plastic, nice color, so it's excellent for shaping. But to be used as an axe, to be used as a arrowhead or spearhead, has troubles because it has a poor edge holding, which means that the mechanical properties for mechanical applications are really limited. Then, of course, as every metal, also copper can be cold hardened. So by deformation, by hammering, can increase the resistance, the mechanical resistance, then can become a better tool for certain applications. But the more we increase this hardness, this mechanical resistance, the more we embrittle the copper, and then we risk to have failure because of breaking of our tool. And then this leads to another aspect, which is simply theoretical. So I understand that what I'm saying can't be proved, but it's just a logical assumption that I propose to our community, and is that once we are smelting copper, sometimes we smelt copper from ores which are richer in other elements. An example, but this is just a poor example because I'm not putting other elements in this list, is with arsenic, antimony, bismuth, silver, zinc, tin, lead, but I could add nickel, cobalt, iron, and so on. I just introduced here those typically self-diffusing into the copper. And then I imagine to be one of the ancient smelter, and I see that if I smelt copper from one specific mine, I have a copper quality which is more resistant than another one. I don't know why. I just know that from mine A, I have a copper which looks more or less the same as a color. Anyway, after oxidation, it looks really the same. But which has a better edge holding. It is better for applications like arrowheads, knives, daggers, and so on. And then, of course, I start to favor this kind of ore, and then the mine, then another mine from where I have a purer copper, but I don't know about that. And this has limited and lower mechanical properties. And I mean, if we look to a list of the principal copper ores, then we notice that we have a lot of traces of other elements. And also we have elements that can be introduced in the alloy. You see, we have lead, zinc, we have often we have arsenic, we have silver, we have tin. And then once we look to practical examples in archaeology, I just selected a couple of examples, but I know that I'm talking to a community much more expert than I do, because I'm not an archaeologist, but I worked a lot since the last 30 years with archaeologists. And I wanted to give some examples, just to move slowly to the last part related to arsenic too. And then, for example, in this case, I have two publications that I propose. And one is about early Bronze Age armbands from Switzerland, and the other one is a practical technical investigation we made, inspired by the previous one, where we propose the usage of tin oxide as the source of tin in voluntary alloys of tin bronze alloys, and also as a marker to understand if this is an early alloy and the amount of recycling that this alloy has suffered. And entering the specific examples, for once I study some ancient object, so this is one of the armband from Switzerland. The corrosion is one of the most fruitful areas of information for trace elements, because in the corrosion layers, this is the corrosion layer, this is the metal, there is a concentration of all those minor elements that usually are more difficult to be detected in the alloy itself. So if you look at this picture in these little areas, but there are other pictures where this is better visible, we have inclusions of tin oxide. But if we look in the corrosion, this tin oxide is much more visible as a crystal. So this is an indication that this tin oxide was introduced as an oxide. But this is not the result of the oxidation of the alloy. It's something which was pre-existing, because the oxidation of the alloy is identified here and is a mix of nanoscopic crystal of tin oxide mixed up with the copper oxide. So if we are looking for information on how the alloy is made, which raw materials have been used, this is a very important source of information. But look, these are the other information we can find in an alloy, which is going far beyond the classical investigation, the classical characterization we can make. And these also support the usage of simpler techniques like scanning electron microscopy, instead of going to more distracting and more precise, of course, and sensitive, but probably less useful techniques like ICP or XRF and so on, because here I can identify and determine what is the size, the position, and the nature of the inclusions. And as you can see here as well, we have large tin oxide inclusions within the alloy, which means that this was introduced as a source of tin, while the sulfides that we have here are copper sulfides, and this is the evidence that this copper was smelted from copper sulfides. But other examples to show another information. This is an inclusion, an original inclusion, where we can find the traces of cobalt, which is one of the elements typically found in copper, nickel, antimony, and tin. And this alloy, which is like the previous one, is another armband, and this is a tin bronze. But in this case, there are no traces of tin added as an oxide, and the amount of tin in the alloy is lower, it's around 1%, then we can assume that this tin was not voluntarily introduced, but was already part of the ore and then found in the ore. So this makes a lot of difference, because create a different plan from the artisan. This is another example of distributed elements, and as you can see, we can really determine that silver and antimony were part of the copper ore, while tin, in this case, was added. And I have many other examples. This is antimony alone, which was creating also specific phases. So this alloy is an alloy of copper antimony, where antimony was not introduced, but was already part of the minerals. So we can really say that it's possible, if we know where to look, to find out when the alloying element has been voluntarily added and when the alloy element entered into the copper lattice due to the presence, the preliminary presence in the ores. And this is important information for archaeologists, but it's also important information for the impact on earth and environment. Because if the element is, for example, arsenic, because we can talk about antimony, which is also poisonous. I mean, poisonous, lead is poisonous. I mean, we have a lot of metals which has an impact on earth and an impact on the environment. But arsenic is the one with a specific problem. The boiling point by sublimation is lower than the melting point. So of course, if we think about smelting arsenic, we will produce plenty of vapors of arsenic and no arsenic at all solid. This is the same problem experienced with zinc. But we know that zinc was introduced voluntarily in the copper during the 1st century BC by cementation. And we have no evidence about this process for arsenic, maybe because we didn't look for it, or maybe because this didn't happen. We don't know. But we know one thing, and we will say this after all. If you look at this phase diagram, we know that this area is the area more interesting for the alloy. So we can assume that up to nearly 8% of tin inside the of arsenic inside the copper is possible. But then we need to understand how arsenic is stable inside, because if we assume that arsenic is evaporating, is sublimating at a little more than 600 degrees, of course we can ask ourselves, but when I'm thermal treating, annealing my alloy, what am I doing? Am I losing some arsenic? What is the evaporation rate of arsenic from the metal? And when I'm remelting, because you know that metal are used to be recycled ore too, am I losing some arsenic? Well, we have different studies, not easy to be performed, and then with controversial results, but we can say that the volatility during remelting is there, but not so hard. And we made some experiments, so we saw that the amount of arsenic lost during remelting is very limited if we work in the correct conditions, which means closed crucible and reducing atmospheres. And the volatility during annealing is nearly non-visible for the short term of annealing. What is dangerous is the volatility of the arsenic oxide, because during annealing we form arsenic oxide on top, and the arsenic oxide is also sublimating, and in this case we can have a superficial reduction of the amount of arsenic. And then arsenic is not that small, and the diffusion rate inside copper is not that fast, and therefore we can assume that there is a limited risk of reduction of the content of arsenic from the core of our metal during thermal treatment. As I promised, we have some experiments with a limited amount of arsenic inside, and we noticed that arsenic is distributed in phases. These phases are present in the ash cast, but can be reduced after a simple annealing, not because of arsenic loss, but because of simple arsenic dissolution into the copper matrix, forming the arsenical bronze. And of course, if we look at this concentration of arsenic on the top of the surface of the ingot, this arsenic, it's probably lost during annealing. I say probably because it's not sure 100%, but we can assume that a part of this arsenic, but is only limited to the surface, will be lost. And of course, once we have oxidation, this will also create other troubles, because oxidation will increase this evaporation rate, but still remaining in quite a limited amount. But we have, of course, information about ancient arsenic mines, but not that as ancient as copper mines. Arsenic is commonly present in copper and iron ores, and then during the treatment of these sulfides, as it has been shown by the previous conference, it is possible to assume that some arsenic is polluting the atmosphere. And we have arsenic-rich fumes, which can become very, very dangerous for people, for those working. And it's not that strange that smelting processes were also always performed far from the community, not close to the community, because the pollution was evident since the beginning. And not only due to arsenic, but also due to the production of a lot of sulfur-rich fumes, which create acid rains, destroy the nature, and so on. And also, this is a suggestion for archaeologists, and I would be really pleased to give my full contribution. It might be fine to look for cementation techniques. We can discuss about this, but if we have cementation techniques proved, for example, in the 4th or 5th millennia BC, then we can really think that arsenic could be introduced as an alloying element. Otherwise, we can remain doubtful and consider more probable that arsenic was already present in the ores. And what are the evidences of arsenic? Well, due to the present presentation, I feel that this is the only thing I want to talk about. But let me say that mythology is very important. Hephaestus is a powerful god, is the god for the weapons of heroes and other gods like Ares, for example. But Hephaestus is also considered the god deformed with severe damages in his body, and is always working far from the others under a volcano. So the mythology is giving to us hints related to, for example, the possible arsenic and lead poisoning, and also the deformation due to the constant work with the hammer, which is heavy, and also the need to stay far from other people. So mythology is probably referring to something that was observed on the metal workers when arsenical bronze was more common than thin bronze. Just a last slide talking about voluntary or natural alloys. Well, taking some assumptions, so not all mines contain the same elements. Tin can be added from tin oxide, or more rarely, because it's rare to find tin in the copper ores, can enter as an element from the ore. Zinc and arsenic can be added by cementation, but we have proof of zinc cementation. We don't have any proof, and we don't have any evidence of arsenic cementation. All can diffuse, and we have the existence of specific alloys at a certain period. So if we consider that in a certain area, certain geographical area, for a period, we have only or mainly arsenical bronzes, it means that there was a voluntary selection of the ores, maybe not being aware that they were producing an alloy with that specific element inside, but they were aware that using this ore from that mine, they produced a metal that had better characteristics than the pure copper or the copper smelted from other mines. And I think that this makes clear the answer to the question at top of this slide, which voluntary is always the answer. Because the moment we make a deliberate choice, we make a voluntary activity. So we know what we are doing. Maybe we ignore what is inside, but we know what we are doing. Thank you.
Thank you very much, Paolo, for your very interesting presentation, inspiring presentation, giving us to consider the composition of ores, natural composition of elements in the metal ores, and the behavior of people with these ores, selection or just accidentally. So we see that the people really knew what they are selecting and what they are doing. And we have to consider also in our collaboration the regions with specific ore minings and compositions of ores, and to consider the chemical elements inside, and all these also productional processes during the smelting and making artifacts, and especially recycling when we do the metal analysis of metal artifacts, we have to think what happened to these artifacts, because the metal could be recycled before, and the initial composition, of course, is not visible at all. And also the arsenic aspect is very interesting, because arsenic metals were used very active around in the period of 2000 of years before tin alloy appeared. So we have a wonderful hoard in Israel made of artifacts of arsenic metals, based metal of arsenic, and it's fantastic object. So people use the metal artifacts where arsenic dominated, so which is interesting, but they left all this and switched to the copper alloys and copper tin alloys. So do we have questions from the audience, please? Yeah, Mario, please. Mario.
So thank you very much. I'll start the video as well. We have settlements. We have really enough evidence that smelting activities took place in the settlement. So I don't agree with your assumption that smelting activities took place somewhere out of the settlement. So just, I mean, if you just think about Hala Sultan Teke on Cyprus, where we have a huge, massive production of copper in the settlement area. So this is, yeah, unfortunately, the things are not that simple. And the other,
yeah, you're right. You're right. I was more talking about general. So I agree with you. So I don't.
Yeah,
I'm totally agreeing with you. Yes, of course.
the other remark that you said about measuring the corrosion layer of the artifacts. I mean, I'm not sure, because you know the ratio of the elements that you have from the corrosion layer is not corresponding to the real alloy
this is
inside
true.
inside the object.
No, this
So
is true.
is there some kind of method that you can, you know, if you're not drilling but just taking the corrosion composition, can you somehow reduce this to the original ratio of elements in the alloy?
Well, what you're saying, okay, thank you for this question, because it allows me to explain better what was my idea. Indeed, the corrosion has offer the possibility to concentrate certain minor elements, because when you have the corrosion process in soil, copper is the main element diffusing in soil, and then you have copper depletion, which increases the concentration, the relative concentration of other elements. This, of course, makes all XRF analysis on the surface of corroded objects useful only as a qualitative investigation, not as a quantitative investigation. And the only possibility we have to use simple corrosion as a source of information for the composition of the alloy, of the base metal, is if we know what is the nature of the soil, and then we know the diffusion rate of copper into the soil. If we don't have this information, my humble suggestion is that you go to the metal and you analyze the metal. And this is why drilling, for example, creates a huge problem, because while you're drilling, you remove part of the corrosion, and of course you need to be very careful to separate the metal from the corrosion. The best method so far is using cross sections to make an investigation. So
Yeah,
it's,
this is rarely the case.
Yes, but during the cross section, you risk to not see certain elements. I mean, depends which kind of compositional technique you use. If you use EDS, which is the most common one, everything which is below 0.5% it's really hard to be seen and quantified. If you use WDS, of course, you can go further because you have a sensitivity up, I think, the starting from 50 ppm. So of course you can have these. It depends also what is the use of an analysis, because if you want to use even the smallest trace element, not the best investigation method. If you just want to have information about the main elements, then it's okay. Corrosion, I mean, what I do in the corrosion is, as I have tried to explain, on one hand, try to understand what is the origin of the alloying element. So was added or was already part of the metal first. And second, if I have the doubt that maybe some silver or some arsenic could be part of the alloy, but in very low amount, too low to be precisely measured by EDS, I know that I can find them with the measurable concentration in the corrosion. So the corrosion allows me to say the original ore contained these elements and that element, but I cannot measure the quantity of the element inside.
Yeah, of course. Yeah, I just wanted to say, because we all knew these measurements from the surface, which show that objects have like 20% of tin, and this could not be the truth. So it's just
absolutely.
Yeah.
It's always well, funny, but also sad after 30 years of work to see that people continue to make statistics on surface analysis, which are completely meaningless.
Yes, I agree completely.
I see Matthias Mehofer, which is agreeing too, with a nod in the head. So yeah, Matthias, it's a long time we don't meet, so hello.
Thank you so much.
Thank you, Paolo, very much.
It's my pleasure, my pleasure.
Yeah, very interesting. Really, indeed, many thoughts for the discussion at the end of our conference. So, and now I want to invite our dear colleague Giovanna Frenghi, who is talking about the long view of the environmental effects of copper production. And we are very looking forward to hear Giovanna's presentation. Giovanna, please.
Okay. The screen is shared?
Yes.
Okay, great. So I work in experimental archaeology, and specifically with archaeological metals. I've spent years casting bronze and other metals and smelting copper and iron. This work was done as experiments and as part of teaching metallurgy and demonstrating at events. Few of us in this field think a lot about the environmental impact, either in the long term or the short term, of these activities that we do. We are aware of the impact on an industrial scale and have some familiarity of the effect in the ancient landscape. So last year, I began to explore the environmental impact of early metal industries, drawing on samples from modern mining data and archaeological cases, and exploring the use of experimental work to examine this. I want to make some points about how valuable experimental metallurgy can be to other fields of archaeology, such as environmental assessment, and also for field archaeology. The environmental pollution and debris created during the metallurgical experiments is rarely sampled, but it can give valuable data that can be compared to ancient sites. This data can be used to understand a sense of scale regarding how much work was done and possibly for how long a site was in use. This is in addition to environmental effects. This paper is not only relevant to research in prehistoric metals technology, but also illustrates the long view of metallurgical industrial waste. By understanding the environmental impact made by Bronze Age metal industries through both ancient technology and in modern experiments, we gain a better understanding of the greater long-term environmental effects of these activities and an understanding of how these issues might be recognized in the archaeological record. In modern copper mining operations, pollution from extraction and refining sulfide ores contaminates soil and waterways through processes of extraction, leaching, and smelting. This results in long-term environmental impacts that are toxic to nearly every living thing. A well-documented example is the Flambeau mine in Wisconsin in the United States. Oh, it went too far. The open cast mine was in operation for 4 years from 1993 to 1997. Several years later, the surface water samples tested in 2004 and 2008 showed elevated levels of copper, 10 times the standard amount allowed for water, and twice the maximum standard of zinc. This is in addition to manganese, zinc, sulfate, lead, chromium, nickel, uranium, aluminum, and arsenic. As a result, the stream leading to the Flambeau River was almost devoid of life, including vegetation and fish. The groundwater was also affected. The mining company was in violation of its contract that included environmental impact statements. The company was sued and lawsuits continued into 2012. 14 years after the mine ceased production. Now, there are several early copper mines found in Britain and Ireland, and processing sites there are difficult to find since ore crushing usually occurred near the mine. However, there is no environmental evidence of smelting, and this is probably because smelting was done in crucibles or another technique that contained the slag and pollutants. The leftover crucibles could have been ground up and used as grog to make more crucibles or furnaces, and thus eliminating any environmental evidence of smelting activity. In Europe, there's evidence of copper production in the form of elemental pollution in the ground, both as a result of direct contact of metal and ore elements and byproducts in the soil, and also from airborne particles that were redeposited. In the Eastern Alps, preliminary research examining sediment cores taken from Lake Leopoldstein revealed trace elements that identified activity associated with copper that ranges from Bronze Age to the mid-medieval, or 2070 BCE to 850 in the Common Era. In addition, other studies have concentrated on the analysis of slag and furnace residue. Research in southwestern Europe included atmospheric studies from cores taken from peat that revealed airborne pollutants such as lead that are associated with early copper metallurgy. Similar studies have been undertaken in the Great Lakes region of the US. There is early evidence of copper mining in the northern US where the indigenous people of the late Archaic period, 6,000 years ago, extracted copper in the area around Lake Superior. Although the copper found there is native, that is, it's in its pure state and it needed no smelting, the copper needed to be heated in order to work with it. This process of annealing the copper oxidized the metal, and its trace elements of lead and silver were released into the air, where it was redeposited in the soil. Evidence of this contamination is still evident. Experiments utilizing soils with contaminants similar to those created during copper production were conducted by Ardestani and Van Gestel in 2013. These showed that crop growth and animals were affected. Barley plant height was dramatically reduced from 13 to 15 centimeters to 6 to 10 centimeters high, and seed production was more than halved. The heavy metal content of sheep and goats grazed on modern mine sites was also high. 24 goat skeletons that were examined contained significant amounts of copper and lead. In addition, all products such as milk and meat were contaminated. This leads us to the value of experimental archaeology as a part of the future in this area. Experimental archaeology is one of the fastest growing aspects of archaeological studies. EXARC lists over 500 open-air museums worldwide where demonstrations of past activities are performed for visitors on a regular basis. In addition, there are over 100 universities that offer experimental archaeology programs that include undergraduate, master's, and PhD degrees. There are also independent student societies that recreate historic and prehistoric activities. These programs often include specific courses in metallurgy. I firmly believe that environmental concerns should be included in every experimental archaeology course that involves metallurgy. In addition to academic and institutional programs, there are independent researchers and hobbyists who experiment or practice early metallurgy techniques. An online search using keywords Bronze Age experimental casting produced thousands of videos on the subject. Academics and members of the public engage in metalworking activities for a variety of reasons: for research and publication, to understand ancient technology, to experience the physical actions and sensory experiences of doing metalwork. The locations for metalwork activities range widely from an individual working on their own property, at a site dedicated to archaeological activities such as open-air museums or university, or at public events held in parks or other public areas. I would mention that many people who are unfamiliar with metalworking as a practice will often attribute the place where it occurs as something involving ritual or secrecy, rather than the practical aspects that it creates smoke and debris that most people would not want near living spaces. Also, when pouring metal, it's not a place where people working would want others to congregate. Casting metal requires concentration and coordination between participants, and it's difficult to do when other people are too close. Other researchers working in experimental archaeology do not interact significantly with field archaeologists. Because of this, information about how and why to position a furnace, where to put the bellows, and organizing the workspace is rarely communicated to the people who excavate those spaces in antiquity. Experimenters often consider aspects such as the direction of prevailing winds, how those winds will change throughout the day. These are important details when there's a possibility that smoke and fumes could be directed towards the person who is pumping the bellows or towards dwellings. Such ephemera is invisible to the field archaeologist, who might guess that furnaces were positioned because of social structure within the settlement or to hide the practice from others. And what happens after the activity is completed? Is it cleaned up afterwards, leaving no traces of activities? This could be the case in experimental work done where the debris is taken back for analysis, but also in the case of public areas where work areas are often required to be restored to their condition prior to metalworking activities. Or is everything left in situ? This might be also the case for research in which taphonomic processes are being researched, or if the site is one where activities are conducted on a regular basis, such as at open-air museums or in teaching workshops. There's also the possibility that a site will be left in order to excavate it later. In addition, field archaeologists are better able to interpret a metalworking site after they've seen recreated examples of furnaces and metalworking activity. Are environmental samples taken? This would be an ideal situation that would yield ongoing data about environmental changes that occur with multiple metalworking episodes. These questions provide for serious considerations for work in experimental archaeology. In recent years, experimental archaeologists have become aware of the interconnectedness of different crafts, how tools and materials of a craft are dependent on one another. Now it's time to consider the interconnectedness of the environment as part of the craft process, not only as a resource to be exploited, but also as an ongoing connection, both in the craft process and the environment of daily life. Last year, the Historical Metallurgy Society invited members and researchers from around the world to conduct experiments in various aspects of ferrous and non-ferrous metallurgy at the second annual Accidental and Experimental Archaeometallurgy Conference in Cranbourne, England. For the most part, participants of the conference had not considered the environmental impact of their work, other than the chemical similarity of the metal or slag they produced to that of similar products in antiquity. None had engaged in taking environmental samples in their work sites. Some of the participants work in open-air museums, including Butser Ancient Farm in Hampshire, England, and the Ancient Technology Centre in Cranbourne, England. During a conference session, participants eagerly discussed the environmental aspects of their work. These were things they hadn't previously considered. The discussions at the Metallurgy conference made them aware of the significance of their work to environmental studies, and considerations are underway to incorporate soil sampling as a part of the chaîne operatoire of experimental archaeometallurgy. All these points lead to a need to better understand the implications of metalworking in the environment. Experimental archaeology and open-air museums provide a unique opportunity of providing samples that can be compared to archaeological materials. Environmental analysis of metalworking sites that have been used for a limited number of times, as well as ones that are in continual use, can provide valuable data about changes made by pre-industrial metalworking practices. Since I discussed this idea last year, I've been in contact with different individuals and groups about taking environmental samples with records about the frequency of use and the length of time for different activities. XARC has also expressed interest in seeing this as a project. Of course, this will need organization and funding, but I believe that this is a project that will yield valuable data and raise awareness of the environmental impact of small-scale metalworking activities. In conclusion, it's hoped that combining environmental research with experimental archaeometallurgy can provide a more holistic overview of the prehistoric environment and the practice of metalworking. The data provided by experimental work is valuable to other fields of archaeology, including those studying the long-term effects of copper production, as well as how it was located in the landscape. Acknowledging the environmental aspects of pollution caused by metalworking can give relevant information about current environmental issues. These will lead to meaningful discussions about human activity and its role in environmental changes. Thank you.
Thank you very much, Giovanna, for your presentation and your experience in the experimental archaeology was very important. Important suggestions for the collaboration with archaeologists who are doing archaeometallurgy and connecting these two fields, experimental processing, experimental archaeology, with the questions we want to analyze. So it's really inspiring what are you speaking about. First of all, I want to ask the audience if there are questions to Giovanna. No. So maybe we will leave also questions for the final part of our conference. Because now we have to move forward then to the next presentation given by Thomas Zacher about analytic copper smelting pits, human health and environment, and possibilities of research on the Western Carpathians. So welcome, Thomas. Thomas? Thomas, are you here? And
Hi.
hello, Thomas, are you here?
Yes,
Good. Welcome. We're looking forward to
thank you very much. Thank you very much.
Giovanna. In the meanwhile, till Thomas upload his presentation. Giovanna, can you hear me?
Yes.
Yes, I have a question to you. So as far as understood, the metallurgical activity was carried out only by really limited group of people. So you mentioned that the maybe a couple of persons, 2 persons, not more, because it could not be surrounded by the society, because it was dangerous. So that means that maybe really we have to think about really a little group of the society who did it. I mean, in a copper and bronze ages, it was a limited activity, probably. What do you think?
It wouldn't necessarily be limited to a couple of people. You could have a larger team working. But the thing is that the more people you have, the more you have to really choreograph what you're doing. You have to know when you pick up the crucible, you have just seconds to put it, move it to the mold and pour it. And you can't have somebody standing in the way. But you do have people working at the bellows and maybe a second person. If the crucible is heavy, a second person to help lift it, another person to skim the charcoal off the top. So you do have small groups, but they, having other people standing around or doing other activities just doesn't work.
Okay. And how long do you think the person need for being contaminated through this activity, smelting metal in open air, for example, not in closed room, for example? How high is the possibility to be poisoned? What do you think?
From the more recent research, and the redepositing of atmospheric lead, it looks pretty high. I mean, the immediate problem is always carbon monoxide. That's just a constant hazard, and that's not something that you can find in the environment, but it would make people immediately aware of pollution, contaminants, even though that's ephemeral. It would have it'd give you a warning about things that could possibly be in the air. I doubt that people in the Bronze Age would think about uh, inhaling lead or metal oxides, but they would be aware of the carbon monoxide, the smoke, and the effects it had on them.
Mm-hmm. Very interesting. Yes. we have to think of these details when we ask our questions. Sometimes we, miss some very important details. Okay, Thomas, what about you? Where is your presentation?
You mean now my presentation?
We cannot see the presentation.
But now is I am here. I am at 11, or
Yeah, we are too late because of the technical issues at the beginning. I was too late, but don't worry about it. Just
okay.
it's okay. We need your presentation. Yes.
Okay.
Upload your presentation, and we have a comment from Justina Baron.
Yes.
To all of us, Justina Baron has a comment on Giovanna's talk, where is interesting example of reinterpretation of fences surrounding a Bronze Age settlement in southern Sweden at this time. They are considered to protect the area from toxic fumes. So, and thank you for the interesting talk, says Justina. Good, Thomas. Thomas, we are waiting for your presentation.
Yes, I need 2 minutes. Sorry.
Okay, good. So it's interesting comment of Justina. Thank you, Justina, for this. Considering the spaces where metallurgy was done, yes, how it looked like actually. Was it separated from other areas of settlements, or was it directly inside? And here it's really this example of this type is interesting to take in account about the separation, surrounding protection, and so on.
I hadn't heard of that, but in England, we've seen a lot of places where the metalworking occurs outside of bank and ditched areas surrounding settlements. And it's in the literature, it's usually attributed to being ritual or wanting to hide the practice from anybody who is watching. But it's probably much more practical consideration that being outside the settlement area would produce fewer fumes and smoke going into where people were living.
And when you are experimenting, you don't wear masks or something. How is it with modern experimenting? You also can inhale with vapors, etc. So it's interesting. You are not protecting or people who are melting metal artifacts, metal artifacts. They are not wearing masks. They are not protecting themselves. So the level of these vapors, I don't know how high they are actually.
Yeah, it's something that people doing experimental work hadn't really considered a lot. Some groups do it completely in costume, wearing Bronze Age type clothing, and others are wearing modern leather and clothing and face shields. But very few people wear masks or protective equipment for breathing.
Why this idea came to the reality to analyze this intoxication during the bronze melting? It started with 2021 as the article was published about combustion from the human feces, mycelium feces, and it was lignite, so which indicate the pollution, the intoxication of human who probably were in touch with metallurgy, active metallurgy. So it's really worth to consider this question and to try to go forward using modern methods. So Thomas, thank you. We see your presentation.
Okay, super, super. Okay, now I am ready. Also, thank you for the organization of this online conference and for the invitation. And I will now short present my new excavation and possibilities of research in the Western Carpathians region in context of human health and environment. Site Horná Myčina is located in central Slovakia, in Zvolen Basin. It's here. It's a meadow in the forest at the transition between the uplands and highlands or middle mountains. Also here is my site. It's here's meadow in forest, and here is view on the Zvolen Basin. It's here or here.
Thomas, excuse me, Thomas. We do not see. We see your slideshow presentation, but not in show, not in a slideshow regime. So we cannot see your mouse and your maps, etc. We only see the first slide.
Okay. Wie kann ich das machen, damit ihr meine Maus seht?
Öffne die Präsentation auf deinem Bildschirm in der Show, ja, in Show-Regime auf deinem Bildschirm.
Okay, und jetzt you can do.
Yes,
you can
yes, now it's okay. Yes.
Okay, good.
Yes.
Okay, sorry, that's
No problem, no problem.
Okay, here is my site. It's here in Zvolen Basin in central Slovakia. Here is also here. Site is localized in transition between uplands and highlands or middle mountains. Also here is Zvolen Basin. It's here. Here is uplands, and here these mountains. It's so highlands in Zvolen Basin. Also, it's not primary agrarian region. During the geophysical survey, we found 30 objects or fissures. That's all these black points. During prospection, we found pottery and ore and slag and a few little copper ingots. Here are copper ingots, ore, slag, ceramic. That formed all amateurs with metal detectors, and we do it the excavations here in this area. Excavation in 21 and 22, we found storage pit. It's here. It's little storage pit and furnace pit here. 1 meter here from storage pit. Here, this black area, it's geological natural fractures. View here is smelting pit. Here is forehead or auf German Vorgrube. And here it's not excavated. Was our storage pit. Here is smelting pit. All these gray stones are ores or fall ores, and here is forehead. The deep of the furnace were 40 centimeters and dimensions 80 by 60 centimeter, and dimensions forehead were 100 140 centimeter here. Here, this part, it's destruction of smelting pit. Here's no more look at the smelting pit here and here. This is natural fracture, and here were forehead. Now here many views. Here this part we don't know if here were an outflow or is it only a natural geological fracture that and in smelting pit we found many layers with smelted ores. It's here, and it has been used several times. This was confirmed by our C14 dates, which is not exactly the same. By the excavations we found in settlement pit fragments of crucibles and ores. Many pieces were analyzed. It's local failure or failure ores, and by archaeometrical analysis, by the first archaeometrical analysis, they are showed it's failure type of copper from Western Carpathians after Schubert, this type of Handlova. Also, it's called after eponymous copper hoard from Slovakia. It's not antimony copper or pure copper or copper from Bulgaria, Ibunar. It's local failure from Western Carpathians. In forehead, we found many big crucibles. They are many in 30 centimeter big, or they are really big crucibles. Dating efforts and dating is 38th century before Christ. It's the same date from smelting pit at settlement pit, and it's this C40 dating is very important. Well, it's first smelting pit from eastern part of Central Europe. Here are many analogies after Timberlake. How couldn't see this smelting pit or furnace pit? Many experiments haben gezeigt, dass das funktioniert und dass das möglich ist.
Many experiments shown that it is possible, so it proved the situation.
Yes, thank you for your English. And now excavations this year in summer, we will find a new or the other smelting pit. We drilled all of our geomagnetical anomalies, but we didn't find any new smelting pit or furnace pit. We found only settlement structures with fugers, objects, pits. Here is house, rest of house, and in one settlement pit we found secondary depositions of metallurgical waste. Also the same material from the same material from smelting pit. I mean, smelted ores, crucible fragments, and many layers with ashes and charcoals. It is interested. It is very interesting. While we don't found here in smelting pit any charcoals or layers with ashes or so. Many little charcoals, they were used for CFC40, but not layers or so. And that is very interesting and important. These metallurgical waste were deposited in 20 meter in one settlement pit. If from critical or from hygienical, we don't know. Here one view. This is settlement pit with layers of metallurgical waste, copper, and it is here, and smelting pit is here. So that's our new excavations this year. And 10 possibilities for the future research, human health and environment. We can analyze it. Soil from settlement, okay, it's not a problem. We can analyze it. Animal bones from the settlement. We have many pieces. They are very little, but okay, it's not a problem. But in this time, from this region or area of smelting of copper or local failures, we don't have any skeletal remains of this late Lendl culture or Rudanice group. We don't have any skeletal remains. They are only at a few settlements in western part of Slovakia, Hungary, and Moravia. But in this region, we don't have any skeletons. Also, we must found any skeletons. But in this culture, in this time, are not the regular cemeteries or so. Also, that's the problem for the future research. Numero one, and the other problem we can pollution in peat bogs on pollen sites in Western Carpathians, but in our interesting area we have only 1, 2, 3 or 2, 3 peat bogs which we can analyze it. I don't know if in this peat box our time sequence is. And other peat bogs in the Western Carpathian, they are too far for our questions or for our analysis. And in not far from our settlement here, we don't have any peat bogs. Also, we cannot reconstruct the environment and impact metallurgical impact on the environment, and that's our problem. That's our problem for this research. And the same situation is in Bronze Age. Is in Bronze Age. We don't have here any skeletal remains or cemeteries for our analysis. Also, it's now from my side, and thank you for your attention. Und ich freue mich auf die Fragen. Thank you very much.
Thank you very much, Thomas. You presented a very interesting site, which is, I think, only 15 kilometers away from the very important copper mine site. Yes, Thomas?
Yeah, yes.
Which
Our
site?
mining sites, they are here.
Yes.
And 3 three big copper mining sites. One is big, it's Spania Dolina, and two here and here. They are a little. They are a little. But for our questions, we don't have here in area in Zvolen basin or here we don't have here any skeletal remains or cemeteries.
Yes, it's great you gave some aspects about their challenges, you know, where we have difficulties to answer our questions. So this is a good point, I mean, but the site itself, I think it has a great potential to analyze the pollution and environmental questions. And especially we have here also very interesting situation with regard to metallurgical activity in the copper age, so in the early stage of the metallurgy. And we see local metal residues, but we also can expect for further investigations in the future. And as you mentioned, also animal bones are, even if they are fragmented, we can be analyzed, and other aspects can be investigated too. So we not always have a settlement or burial site with all elements which we can use for our analysis. So that's why I mentioned we have 60 sites. You know, we can select from one site one part of information, from another site another information for our questions. So it's, I think it's impressive what you have shown, but I see on chat, I see Matthias. Yes, Matthias is asking, maybe he's asking, did you find smelting slags, Tomasz?
Yes, we found smelting slag, but not many. Only 3 pieces we found. Only 3 pieces. We found only 3 pieces.
And Matthias is also asking if yes, so you find, but can you reconstruct the process, kind of co-smelting or just smelting of oxidic ores?
No, we don't have found oxidic ores. Only sulfidic ores or phalor. We don't found malachite or azurite or so. And co-smelting and remelting and roasting, this process will be now in the next years reconstruct.
Yes. So
we need time and money.
Yes. So I'm very looking forward to hear more from this side. So thank you, Tomasz. And now our last presentation in this morning part. Dominika Orashkinova and Tomasz will present Bronze Age sites, metal production sites in Slovakia. And we will know about research, new data, and future perspectives. So please, Dominika and Tomasz, and don't worry about the time. We will, make a shorter lunch break.
Hello, and all, everybody. Thank you for welcoming. Just please, can you confirm me if you can hear me well and see my presentation?
Yes.
Okay, perfect. Dear colleagues, at first, thank you, Agne, for organizing the meeting here today. Even if only virtually, I would be very happy if we see each other also in person. I see quite a bunch of friends here, so maybe next time. We are very glad that we can discuss common topics that, despite varying geographical contexts, hold significant relevance for us. I just would like to highlight that we are staying still in Slovakia. We are just moving a bit forward in time into the Bronze Age. We also apologize for the broader focus of our presentation that didn't reflect the conference primary theme completely. However, within the context provided, you will hopefully understand that it's demanding for us to establish the baseline hypothesis regarding the influence of metal pollution in Bronze Age Slovakia if we like more comprehensive information about the range and socioeconomic importance of those craft activities. Taking a part in such a company of skilled experts, we also would like to take an opportunity to discuss some of the already published and unpublished data, as well as to share updates of our current works in progress. I think this is the best time to talk with you. Well, is it moving?
Not
Yep.
yet.
Okay. The driving force behind the economics of the European Bronze Age lay undoubtedly in the production and distribution of artifacts made of a new, more technologically advanced material, bronze, within the wider territory of northeastern Carpathians. Inhabitants undeniably held a significant advantage. They benefit from proximity to rich copper deposits that have been archaeologically verified for surface and subsurface mining, especially in Špania Dolina mining area. While Slovakian copper resources may not have been as crucial, it appears that during certain periods they could have played an important role for surrounding areas where natural deposits were absent.
Dominika, excuse me, do you show the second slide now, or you are still by the first? Because I'm not sure if the slides are switching.
This is the second one. So after
we don't see it on our screen. We see on the first slide, Dominika.
the introductory one.
Yes, the first introduction.
I think I get the same technical issue as my colleagues before.
Yeah.
Well, I will just try to
Be quiet, don't worry. We have time. It's everything fine. It's okay.
I will try to share my whole whiteboard share. No. This one share. Okay, this time you can see it.
Yes, perfect.
Okay, perfect.
Thank you.
So the fact that the multi-products exchange trade network was sensitive to changes while depending on the whole range of circumstances is apparent from the results of chemical, but also from typological analysis of bronze objects found along the presumed routes crisscrossing the Carpathian Basin. All those oscillations are also well reflected in the settlement strategies in relation to proximity to raw material sources in different periods of Slovak Bronze Age. Therefore, we might assume that they could partially suggest the intensity of local production from local deposits or the capacity to compete with other significant European mining centers, or better connectivity to trade networks where they could also participate with other goods due to a higher overall level of economic prosperity. In this context, we can declare two main milestones in Slovakia. First one is during the early Bronze Age. You can see the situation going on here. And the second during the late Bronze Age. You can see the situation here. Those were alternated with the phases of a regression and subsequent reorganization during the late Neolithic and the Middle Bronze Age. As researchers specializing in the Bronze Age Slovakia, we have to admit with a heavy heart that our state of systematic research on metallurgy, which is most likely the cornerstone of then community economies, is underestimated. On the right side, our overview that the key publications from Slovakian authors that attempt to synthesize the presumed socio-economic significance of a local Bronze Age metallurgy. On the left, here, are selected works delving into the geochemical properties of local ores, along with the artifacts that are crucial for understanding the impact of Slovak ore mountains copper deposits in European context. Of these should be highlighted the most elementary contributions by Markus Schreiner's works and the German Mining Museum in Bochum. Geographically, at least the last mentioned focused mainly on Špania Dolina mining region. You can see here the area, and compared the data mostly with the artifacts from Western Slovakia. It is important to emphasize that the lack of archaeological materials does not cause the imbalance. The truth is that the evidence of metallurgy spans nearly every region and period in Slovakian Bronze Age. Even if we know that the metal crafting regularly occurred at the settlements, our understandings remains limited regarding ore sourcing, potential smelting processes, the extent of the artifact remelting, and the final product's distribution. Be not only skeptical. There is a lack of data. There is also an excellent opportunity to fill the gap. In that regard, we would like to stress the area of Eastern Slovakia in early and Middle Bronze Age. Referring to our first slide showing the presumed social fluctuations, we are at the first of the pivotal peak at the end of the early Bronze Age. This coincidence with the so-called Ottomani Fuzeshabon cultural complex, characterized by establishment of a dense settlement network consisting of the fortified settlements. Notably, those are concentrated near numerous oxidizing subsurface deposit of a copper minerals. You can see mapping in here there by light orange are those subsurface or subface deposits. To verify all related causalities, we currently chemically evaluate the artifacts from sites Nižná Myšľa, Gánovce, Spišský štvrtok, Košice Barca, and Včelince, along with a small subsample of local copper ores. We apologize that we will only present the partial information today, as our analyses are still in progress. So let's start with the exceptional evidence of on-site metallurgy at probably one of the most well-known sites, Nižná Myšľa. There is probably no need to introduce the two graves of adult men with the complete metallurgical toolkits. You can see them here, probably metallurgists. Interestingly, in the terms of absolute dating, they are the oldest buried in the necropolis that contains almost 800 skeleton graves. Moreover, within the settlement zone was just recently, you can see here, excavated a pit with the remains of pyrotechnic features. In this kidney-shaped pit, measuring 4.5 to 6 meters, were found stone casting molds, technical ceramics with the remains of bronze, as well as bronze byproducts and final products of different completeness. In the surround was also evidence a high concentration of stone artifacts used for grinding, smoothing, and polishing that might point to activities associated to the final finish of the metal products. By means of a chemical composition of small section of local forms of bronze artifacts from settlement and burial ground in Nižná Myšľa, they all showed chalcopyrite signatures. The half matches solely to the Slovak or mountains copper sources, you can see here, and the half overlays with the both deposits in question. It means the Eastern Alps and Slovak or mountains. In their trace element composition, they share the features of early and middle Bronze Age production identified in Scandinavia, Germany, and Hungary. Moving to the next center settlement from the same period in Gánovce, we can presume the bronze melting and casting by micro residues identified on the surface of two stone molds. You can see here. We use the scanning electron microscopy. The chemical composition of these visible particles, notably enriched with the copper, tin, and lead, proves their active on-site usage for casting bronze pins with a double conical head and the rod-shaped objects. The range of intersite exchange at the end of the early Bronze Age is illustrated especially by a mold used for casting the pins with double conical head, you can see here, because this form correlates exactly with the final product, a similar pin discovered in the fortified settlement of Spišský štvrtok, approximately 10 kilometers away. Regarding mentioned fortified settlement from the turn of the early and middle Bronze Age in Spišský štvrtok, the question arises as to whether the inhabitants here, in addition to casting bronze, could also devote themselves to the processing of the primary raw material, copper ore. Our evidence includes sporadic slag here, complemented by earlier reports mentioning the presence of a malachite here, initially in the form of a supply pile in the inner settlement layout found in this zone of the settlement. These might have originated from chalcopyrite minerals oxidizing to malachite between their deposition and the time of the excavation. Furthermore, the discovery of specularite and cinnabar minerals suggest that the potential exploitation and of oxidation deposit within the nearby Rudniany minefield could happen there. However, it's just a hypothesis. That means that drawing a definitive conclusion on this theory remains challenging, as the malachites in question have been lost, and the investigation of the relationship between the slag and the metallurgical processes is still ongoing. We are waiting for the some EDS analysis currently. During the sider excavation, we are still in Spišský štvrtok in 2020. We reviewed the chemical compositions of recognized stratigraphical units surrounding the fortification. The high enrichment for heavy metals like copper, zinc, nickel, and lead revealed, especially in the backfill of the previous trench. Those are these stratigraphical units. You can see them in the bloody red. Supposing that this soil was transported during the early excavations from the inner settlement layout, we can indirectly declare that the metallurgy indeed took a part while leaving behind certain traces of the pollution. Among all, the most comprehensive insight into geochemical characteristics could be drawn from the bronze collection from the settlement in Spišský štvrtok. In the analytical section, we prioritized based, semi-finished, and finished products, the local casting of which is also proven via mounts. We also have marginally included the shapes where is not excluded that they reach here through the active trade exchange. The scanning electron microscopy, you can see the results here, show the impurities enriched by sulfur and iron, which confirms the smelting of sulfidic copper ores from probably oxidation deposits. All were cast from copper, which originates from chalcopyrite, while they clearly represent a chemically homogeneous group without the outliers. You can see here the degree of the homogeneity. Based on the chemistry, the origin of the copper raw materials could be sought mainly in the Slovak or mountains. Moreover, the identical law of materials used in the settlement to cast objects was circulating across Romania, Hungary, Germany, and even Scandinavia at the same time. The values of the lead stable isotopes, they are down, are of great diversity, and in addition to the main group, which is situated here, allow to single out also several outlying values here and here. Within the both extremities, together with the artifacts, are also represented the byproducts, which proves that the materials with the different values of stable lead isotopes were not only imported in the form of the final products, but were also remelted directly at the settlement. This confirms that most of the production originates from the deposits of the Slovak or mountains. You can see the coloration here. However, in the case of the several items, I'm talking about this group, the Eastern Alpine provenance cannot be ruled out completely. Nearly identical morpho-typological objects as found in Spišský štvrtok site were also part of the household inventories in another fortified settlement. I'm talking about the Košice Barca, and that proves their mutual chronological contemporaneity. The close relations are also independently confirmed by the results of chemical analysis, whose outputs are most comparable with Spišský štvrtok bronzes. You can see again, kind of the homogeneous and concentrated group here. These strongly suggest the probable integration within the identical production and distribution networks. Assemblage of bronzes found as a part of the hoard in the house destruction layer in Pčelince can be chronologically considered as the youngest among all I'm talking about, because it contains elements typical for the late Consider phase and correspond more to the Middle Bronze Age. I'm talking about the sickles, those types of pendants, as well as the axes. Two of them were produced of chalcopyrite sourced from the Eastern Alps of Slovak ore mountains, you can see here. And so incorporated a new copper mineral tetrahedrite, which was more likely of the local origin. I'm talking about this particular. And you see more like opportunistic approach in the research. So I'm looking forward if we will get the chance to get a more systematic research. And for these purposes, we together selected several potential sites from Slovakia that could be of high importance in the future to collect all of this information and just layer them one above each other. And from the early Bronze Age, we try to select the sites that they will be close to the deposit as much as possible. So here you can see the section from the early Bronze Age. There is high potential of work with the cemetery in Jelšovce, Matuškovo, and of course cemetery from Nižná Myšľa. Then the settlements, fortified settlements, Rybník, Santovka, Spišská Nová Ves, oh no, the cemetery, I'm sorry, Spišský Štvrtok and Včelince. As I was talking about the Middle Bronze Age, like the more of a regression period, we only sourced out 3 sites, settlements, the Figastranská, Radzovce, and Včelince. And for the late Bronze Age, we sourced the central settlements, Ilia, Radzovce, and Trenčín, where is a very numerous evidence of on-site metallurgy. And with such a hopefully optimistic future, I just would like to thank you for your attention. And we will be, of course, very happy for any kind of discussion.
Thank you very much, Dominika, for such an interesting review of such impressive sites. And it's good to be optimistic, to have in perspective really very interesting objects to investigate, with a huge complex of elements, which are really good for our questions. So maybe someone want to ask something. So Matthias is happy and says that it is really very interesting. So bravo.
We had a lot of work that I want to tell that I think you are just more forward than we are in Serbia or Romania, or of course, Austria. But here in Slovakia, I think the work is everywhere around us.
Yeah, but we have from the very beginning of the early Bronze Age to the late Bronze Age, very interesting sites, but Horst as well, and really impressive burial sites, but skeletons, as you mentioned, Nižná Myšľa. So it's a huge potential to look more in details about metallurgy and impact of metallurgy to the environment and to human health and conditions and so on. It's really a good material. So thank you for presenting it, and I hope we will create a good framework for making it possible to investigate. Thomas, yes?
I will say, Dominika, thank you very much for this very nice presentation. And I will say, and I must say, it's project and work from Dominika. I help it only a little with drilling of bronze artifacts, and I'm busy with consultation, but it's work and project from Dominika.
Okay, congratulations, and thank you once again.
It wouldn't be you. It takes more time, and if so, so I think it's like always about the cooperation.
Yes, of course.
So now, actually, we have a coffee break time now, which should start at 12 p.m. Lithuanian time, our next part of the session. But I suggest just take a cup of water, 5 minutes, okay, because we need a short break. Do you agree with 5 minutes break? Or do you think you need 10 minutes? Is it okay? Can we meet at 12?
Yes, it's okay.
Yes, it's okay.
Okay, thank you. So we meet at 12:15, and Florin, excuse me for being late, excuse for all of you.
I'm here. I'm
Yes.
here. I'm
So
here.
see you in 5 minutes.
Yes,
Okay, we
yes,
got a cup of
okay.
tea or water,
Okay.
and see you soon. Okay.
Okay, okay.
Thank you.
Bye.
O aš tau kaip tik norėjau skambinti. Hello everyone. After 5 minutes break and after such interesting first part of the conference, we meet again to welcome Florian Dodaltan and Victor Sauer to learn about an impressive site of Santana and about questions which are interesting for us in our conference. So please, Florian, please, Victor.
Okay, just a moment. Just a moment.
Don't worry.
Okay. Oops, sorry. What happened?
It's okay.
No.
We see your
No.
slides.
You see my
Yeah,
my
perfect.
slides,
Oh,
yes?
perfect. Yes, perfect.
Okay, okay. Our presentation will consist of two parts. In the first section, we will provide general data about the late Bronze Age megafort at Sant'Anna Cetata Veche, with a specific focus on presenting the metal pieces and the human remains identified at the site. In the second part, our emphasis will be on the archaeological findings that enable us to reconstruct the impact of metallurgy on the environment and the health of the people in the Lower Mureș Basin micro-region. This highly significant archaeological site is situated in southwestern Romania, 15 kilometers west from the Apuseni Mountains here, and 20 kilometers from the point where the Mureș River exit the mountain gorge. The fort was erected on a high portion of the plain, shelter it from the periodic floods of the Mureș River, situated today at a distance of 20 kilometers. The flood control and marsh draining works undertaken by the authorities of the Habsburg Empire during the 18th and 19th centuries have dramatically changed the landscape of the region. The paleoenvironmental analysis, in conjunction with the study of this region's oldest map, unveils the image of a region with a strong tendency towards flooding and marsh formation, especially in the lowland areas. In the same area located today at the border between Romania, Serbia, and Hungary, there are also other massive fortifications. Among this, in the last 15 years, have been archaeologically investigated 8 megaforts, such as those at Cornești. On this map is number 2, Sant'Anna is number 7. Also in Romania, number 5 is Munar. In Hungary, Csanádpalota, and number 3 is Idios Gradište. The absolute dates place all this fortification in the second half of the second millennium BC. The most impressive, now only 2 examples of such megaforts, late Bronze Age megaforts. Cornești is the most impressive in terms of fortified area. A total of 1,722 hectares are enclosed by defensive ditches and earthen ramparts, separating it from the surrounding territory. The ramparts have a complex structure being made of compacted earth within a wooden frame. The amount of wood used in the construction of this fortress was substantial, causing a significant ecological impact to the extensive tree cutting. Another site is Csanádpalota. Csanádpalota is situated at a lower altitude, and it's something smaller, but still reaches approximately 400 hectares. Here, a complex of system of trenches was excavated, serving the purpose of defending the inhabitants and protecting against potential floods. As we will see, what makes the mega fort at Sant'Anna truly special among these sites is not the fact that we are excavating here now. In fact, we have also excavating at Cornești and Munar, but the impressive number of metal artifacts discovered over time. Alongside the human bones identified in recent years, it constitutes an objective that fits perfectly in the theme of our conference. Despite the fact that the impressive fortification of Sant'Anna was marked on the area's maps ever since the end of the 18th century, and some of the discoveries caught the attention of archaeologists since the end of the 19th century, it was only in the second half of the 20th century that the site was attributed to the end of the Bronze Age. The excavation performed in 1963 already provided proof of an ample conflict that took place here. A bronze spear head was found during a field survey, and another one was discovered among the debris of one of the burned dwellings. From this photograph, it can be observed that up to this point, agricultural activities have no significantly affected the site. Since 1960s, with the use of increasingly powerful tractors, a large number of bronze pieces have been unearthed, ranging from bronze belts and socketed eggs to small ornaments. Even if they were not so spectacular for the non-specialist who discovered them, in the collection of the museum in Arad, there are also objects that testify to a local metallurgical activity, among which some fragments of bronze ingots stand out, and you can see number 6, 4, and 7 on this slide. In autumn 2009, we carried out a rescue excavation in the northern part of the site, which was affected by the excavation of a gas pipeline. On that occasion, we investigated the so-called third fortification at Sant'Anna. In that area, it consisted of a rampart built out of clay, wood, and stone, measuring almost 27 meters in width and 2.5 meters in height. The defense ditch was located 8 meters in the front of the rampart, and its maximum opening measured 10 meters, while in depth it reached almost 3 meters. In addition to other archaeological material, human remains were discovered in the moat. The bones belonging to 2 major individuals, males, aged between 20 and 30 years. One skull fragment displays traces of trauma, reflected by 2 balls that have probably caused the individual's death. The absolute data obtained show that they are contemporary with the time of the destruction of the fortification and are placed sometime between 1400 and 1300 BC. During the rebuilding of the third fortification following the first siege that led to the conquest of the fortress, several cremations graves were destroyed. The archaeological inventory discovered is characteristic to the late Bronze Age, suggesting that the cemetery belonging to the community that built the first fortification in Sant'Anna. As for the metal pieces, small ornaments were discovered in situ, as well as an arrowhead used by the besiegers. Other pieces of metal were discovered during field research. The fragment of a copper ingot stands out, is number 10 on this slide. Its isotopic analysis could provide important clues as to the origin of the raw material from which for which many of the metal pieces found at Santana were made. The recent research was carried out within the framework of the LÖWE, Prähistorische Konfliktforschung Burgen der Bronzezeit zwischen Taunus und Karpaten project. In addition to the archaeological excavation, the research effort also included the magnetometric survey on the entire area of the fortification, coupled with LiDAR scanning of a territory measuring nearly 850 hectares. Thus, we have a clearer and more comprehensive picture of the fortification. We know now that the site is comprised of 4 large enclosures, the largest one reaching 130 hectares. In summer 2018, the defenses of the third enclosure were once again investigated with the aim of clarifying a series of aspects regarding the construction method employed, as well as to collect samples for radio dating. The preserved width of the rampart is nearly 20 meters, while its height is 1.8 meter. A 6.5 meter wide and 2.5 meter deep ditch number 1, in this area, or here on this image, was dug at the base of the rampart. A second ditch, 7.6 meter wide and 2.5 meter deep, was identified at a distance of approximately 12 meters from the first one towards the exterior. Another bronze arrow was discovered on this occasion. The excavation of 2019 campaign focused on the so-called fortification 1, is this one, and here somewhere was our trench. In addition to the identifying fortification elements consisting of a defensive ditch and 2 palisades, several human remains were discovered. They appeared among the debris of the burned palisade or in the ditch. Following the bioarchaeological analysis, it was established that they belonged to 13 individuals, children, females, and males, most of them belonging to the male adult segment. As far as the chronology of the Santana megafault is concerned, today we benefit from a substantial amount of absolute data showing that this site was in function for at most 200 years between 1450 and 1250 BC. And you can see also this phase cemetery is contemporary with the fortification. But the fortification suffered 2 destructions. This horizon is the first one, and the second one is here. As we said before, the human remains belong to the first community that built the fortification of Santana. Most of the metal pieces belonging to this community. Let's now escape for a moment from the megafault at Santana to see what the situation is in the late Bronze Age in the lower Moorish region from the perspective of other metal finds and human remains. Another representative site, Bronze Age site in this area, is the Middle Bronze Age tell at Pečka. We use another chronology in comparison with Slovakia, for example, but here you have the absolute data. That's so. Pečka lies just 40 kilometers southwest straight from Santana. Archaeological research at this site has provided perhaps the most important information on the metallurgical activities that took place in the Middle Bronze Age tells in the Carpathian Basin. This demonstrates that before the emergence of the late Bronze Age megaforts, this site was connected to the local raw material resources in the Apusen Mountains. This intense metallurgical activity in the lower Mureș area did not cease with the disappearance of the tells. At the beginning of the late Bronze Age, this is around 1600, 1500 BC, new large up to 40 hectares unfortified settlements appeared. Rescue excavations at Șagu, about 30 kilometers south of Santana, have established that this settlement were also the site of notable metallurgical activities, and you can see on the plan where appears different molds, bronze artifacts, and so on, and also the chronology of this site. During from this site, from 13 pits, have been recovered 28 tempered clay and 14 sand stone mold fragments, primarily for socketed axes and chisels, 18 crucible fragments with traces of crucible slag, 9 cores for casting socketed objects, and a cylindrical furnace. Of course, on this slide are not all these pieces. The cemetery, another site, the cemetery at Pečka site 14, was identified and investigated during 2011. In the almost 8,000 square meters excavated area, 38 graves were identified, on which 24 were inhumated and 14 cremated. Given the 19 carbon-40 data we have so far, we can state that the burial space was used for a longer period of time, from the 16th century BC to 9th century BC. During the 16th and 13th century BC, you can see also the some of them have calibrated carbon-14 dates. So between 16th and 13th century BC, contemporary with the megafort at Santana, we are dealing with inhumation graves, in which most of the deceased were laid in a crouched position. The burial inventory consists of amber beads, bronze items, ceramic vessels, and meat offerings. Again, we note the large number of metal pieces found at this site, and you can see a lot of weapons and different ornaments. Not only finds from settlements or necropolis testify to the incredible wealth of bronze finds in the lower Mureș region, but also hoards or isolated finds. Only in the area of another late Bronze Age megafort, Pečka, with an area of circa 100 hectares. Unfortunately, this site is not archaeologically investigated until now. We have been found less than 3 bronze hoards, the so-called Pečka II hoard. It's not completely on this side, are more than 100 pieces. All these objects are also found in Santana megafort, attesting to their contemporaneity. In order to convince you once and for all of the archaeological potential of this microregion in the late Bronze Age, we also note a few gold hoards. The gold bracelets seem to have been highly appreciated by the local elites. The impressive number of gold, bronze, and copper artifacts discovered at Santana and in the surrounding area may suggest the possible exploitation of the metal deposits found not far from here at the base of the Zaround mountains. In 2019, several galleries of copper mines were explored at Covasins, 10 kilometers east from Santana. This is an image from Covasins in direction Santana megafort, which is somewhere here on this plane. Based on analysis of lead isotopes we will see if they were also used during the Bronze Age or not. Dan Beresh, in his presentation, will complete this archaeological information with data how the metal pollution can be identified in the pit bogs of Transylvania. Thank you very much.
Thank you very much, Florian. Amazing complexes with huge potential to investigate our questions. Very important is, I think, also the huge amount of metal artifacts which has to be analyzed too, in order to recognize the chemical compositions, behavior, interrelationships, and also amount of, let's say, toxic heavy metals inside of these artifacts, how many we have, how is the metallurgical behavior within these artifacts. It's also important. Also human relationship to metals, as we see the hoarding praxis as well, and metal artifacts in the settlements, and also the graves are of great importance to this question of our conference. I don't know, do you have questions, the audience, to Florian and Mario? Does someone want to ask? I don't see any. Okay, so but what I want to ask you, have you done some environmental investigations around Santana and lower region? Have you tried to prove the environmental aspect with regard to really active metallurgical activities?
Until now, no. I work together with Daniel Veres, and he will present you which pit bogs were analyzed in the area of Transylvania. So we plan to continue his project also but he will speak more about this in his presentation.
Yeah, we will have his presentation, which is great. So really a good connection to what you showed. So thank you very much.
And okay, thank you.
We move forward and welcome Mario Gavranovic, Alexander Kapuran, and Matthias Mayhofer. And we switch to the burials now, and specific burials, cremated burials. So it's very interesting to hear about this. So
thank you very much, Agne. I hope you can see the presentation.
Yes.
So I will present some results of our research in Eastern Serbia, which is, as you all know, a region with the most abundant copper deposits in Europe, and copper is actually exploited until the present day in this area, and it's okay. Not switching now.
Not yet. Not yet. No, it was okay. Yes.
Yeah, no, it seems to be.
Mm-hmm.
Okay, so as I said, this is a part of the research in the frame of our project. Here you see the core members of our team based in Vienna, and Alexander Kapuran from the Institute of Archaeology in Belgrade, one of our main cooperation partners when it comes to sites in Eastern Serbia, which we will talk about today. And I can be very proud to announce that a few weeks ago we received a positive answer for the funding of the next 4 years of our research based on the metallurgy, Bronze Age metallurgy in the Balkans. And of course, this would not be possible without this long list of cooperation partners in Croatia, Serbia, Bosnia, Macedonia, museums and research institutions. So basically, we had a couple of key questions when we started our investigations 5 or 6 years ago. The first one was to see if there is any evidence for the exploitation of local copper sources during the Bronze Age, by means of the analytic approach. Then, of course, we also aim to reconstruct the metal exchange networks during the Bronze Age in this area. And of course, can we see any archaeological evidence of social, let's say, stratification, which is based on the metal exchange or metal trade or metal exploitation? We use of course, we are starting with the archaeology as a primary point, in terms of dating and distribution and typology, and we apply trace element analysis and lead isotope analysis. And in this first project, we had over 560 chemical analysis, 280 lead isotope analysis, and 50 C14 days. And as I said, we have now fundings for the next 4 years. We included in our analysis all available steps of the metallurgical production, starting from the ores, slags, of course, if we have some copper ingots, mostly found in hoards, and finished objects. So, but today I will focus on the Eastern Serbia region located south of the Danube River. As I said, the copper exploitation is present until today. And here you see on this simplified geological map the size of this geological body, which is very rich on copper deposits. Here are some modern traces of exploitation, and today we will focus on the sites located just west of the city of Bor. But as you all know, the exploitation in this area started much earlier, with one of the earliest mining sites in Europe, copper mining sites in Europe, Rudna Glava, excavated by Borislav Jovanović, and thanks to the series of radiocarbon dates provided by, among others, by Dušan Borić, we know that the main exploitation of Rudna Glava occurred in late 6th and 5th millennium BC, and it was assigned to late Neolithic or early Copper Age Vinča culture. There is a long list of literature about Rudna Glava. Thanks to the work of Miljana Radivojević, we also know that these early Copper Age communities were not only engaged in mining, but also in copper production and copper extraction here at the site of Belovode. However, little was known about the Bronze Age developments in this region until late 80s, when the Borislav Jovanović, who also excavated Rudna Glava, started his investigations at the site Trnjane, near city of Bor. The reason for this excavation was the number of slag finds on the surface of this natural terrace, which was not fortified. And in the 1985, 1987, he started with the excavations in the settlement area, but this switched, the focus of the investigation switched 1987, as in the immediate vicinity of the settlement site, a cemetery was discovered. And from that point on, Borislav Jovanović focused on the investigations of the cemetery. This was really interesting because up to that point, this was an unknown burial practice in Central Balkan, with this circular stone structures measuring between 1.5 and 3 meters in diameter, and an urn placed in the middle part. Here on the right side, you see pretty much everything what is found in these 43 graves in Trnjane, apart from urns. So there we were really poorly equipped, let's say. No grave goods, very few metal finds, and the vicinity of the site of the cemetery to the settlement led to the assumptions that the cemetery belonged to the settlement. In his publications, Borislav Jovanović described Trnjane as a late Bronze Age necropolis following the burial rite, cremation, and he saw the connections with the urnfield culture. And as I said, he stated that Trnjane is the late Bronze Age necropolis influenced by urnfield culture. And this was actually the state of the research until the beginning of our work a couple of years ago. So we started also with the excavations on Trnjane, and in the meantime, our colleagues from the Institute of Archaeology in Belgrade started also the excavation of the site Ružana, where they also found a sufficient amount of slags and other traces of copper smelting. And in our excavations, in Trnjane itself, we also found a different type of slags in huge amounts, and pottery finds which at the first glance didn't appear to be late Bronze Age. So we were really not sure about this dating proposed by Borislav Jovanović. We didn't find at Trnjane any installations, copper smelting installation, because the cultural layer was severely damaged by agricultural activities. But you know, the slags and the animal bones and the charcoal and provided an opportunity for radiocarbon dating. Then we moved to the nearby site of Čokanjica, where we first did some geophysics prospections. And as you see, this is also an unfortified plateau, and we were lucky enough to find here at least the remains of copper smelting installations and drops of pure copper, very actually immediately under the surface. This is what could be documented in this excavation, some kind of oval clay stone structure with many finds of slags, pottery, and fresh copper drops. So we can assume that, I mean, according to the number of plate slags, which are the final product of copper extraction, we assume that this installation was used in the last step of the purification of the raffination of for the copper. The finds from Trnjane and Ružana and Čokanjica, Matthias Mayhofer did some really good work in the reconstruction of the smelting process, and you know, following the shape of different slag types. He proposed at least three-step production with different waste, different slags. The first one is this block slag weighing up to 3 kilos. And then we have a hooked edge slag, where we assume that the copper was already you know, here in this area. We have remains of the copper, and then plate slags as the last type. So this is actually the you know, state of the research right now. And we assume that these installations were not that big, but they were quite widespread. In every actually settlement in the area, we found very similar traces. And here's some first reconstruction of copper production. Yeah, but really interesting was were the first radiocarbon dates that we received from the settlement area, from different samples, including animal bones and burned weeds and charcoal from the slags, that show that these sites are by no means late Bronze Age, but actually 400 or 500 years older than previously assumed, dating between the 19th and 17th century BC. So in order to, since Trnjane cemetery was excavated completely, in order to extend our knowledge about burial practices, we started with the investigation of another cemetery located just 1.5 kilometers from Trnjane, called Hajdučka Česma, discovered in 1992 with a chance finds of 3 urns during the house building. And we also employed first geophysics that showed very conspicuous concentrations of anomalies, so bipolar anomalies. And after the first test trenches and excavations, we realized that these all anomalies that you see here as a black and white dots are actually graves of the same appearance as in Trnjane, with the circular stone constructions and an urn placed in the middle part of the grave construction. So until now we excavated 14 graves, but the cemetery is much more larger, as you can see on the geophysic picture. The spectrum of urns is quite comparable with Trnjane and some other sites that were found in the meantime, but there are also some peculiarities, you know. But again, the common thing is the very low number of grave goods. So we have only spindle whorls and few lamps and one metal needle. This is all what we have from the graves. As I said, there were some peculiarities because we had for the first time a one construction that served for the burial of 3 urns in one constructions. Then we have one group of graves where we have apparently concentrations of younger individuals buried in urns. And this urn with the lid is the first one where we identify, thanks to the anthropological analysis, remains of 2 individuals in one urn. So some general remarks about the burial practice. We can attest that all parts of the body were present in the urn. We have, in few better preserved urns, we have indeed anatomical layering of the remains, starting from the skull until the lower limbs in the vertical position in the urn. The temperature, the burning temperature was very high. Most of the bones were calcinated and whitish, so this must be 800 and more temperature. We have, after the evaluation of anthropological reports, we can state that we have all age groups, or both sexes in cemeteries. So there is actually a good reason to assume that we are here dealing with communal cemeteries, which are meant to be for all members of society. But again, there are definitely no signs of any kind of wealth accumulation, although they are most probably, most of them were directly or indirectly involved in copper production. And the dates from the Hajdučka Česma cemetery confirmed the previous dates from Trnjane necropolis, with most of the graves spanning between late 20th and early 17th century BC. We did then also radiocarbon dates for some necropolis in the same area of the same appearance, and they more or less confirmed our picture. They are all dating in the same time span, reaching between 20th and 17th century BC, and are contemporary with the settlements. So after all, we can now plot these dates that we have from this region in eastern Serbia, and see that this time span is very good. You have a very sharp boundaries, more or less, with the 20th century, or let's say maybe late 21st century as the oldest date, and the 16th century as the youngest date. And it's particularly interesting when we compare this date to the younger, to the other cremation graves from other parts of Serbia in Morava Valley, or more to the south, except of Ranutovac site. But these are all significantly younger, dating between 15th and the 13th century BC. So if we now kind of zoom out our perspective from this region, and compare this with the dates from the Alpine region, let's say, we can see that our dates from Eastern Serbia are somehow preceding or shortly preceding this boom of copper production in the Alps. Of course, there's evidence of copper production in the Alps also for earlier periods, but when we're talking about the boom about this mass production both in Eastern Alps and in Trentino region, we can see that dates from Eastern Serbia are slightly preceding. Of course, we cannot directly compare these two regions because the amount of the produced copper is much more lower in Eastern Serbia, and obviously the technique of copper extraction is very different, and of course we don't have this kind of burial sites in the Alpine region. As I said, we have a very widespread local production in Bronze Age sites. In every site there's a trace of copper production with these different types of slags. All these sites are not fortified. There's no signs of fortification, so logically there's no need for protection then, although they are producing what we think is a valuable good. What is also interesting that in this whole area we don't have any signs of casting or bronze production, bronze alloying. In general, we have only few bronze finds from this region, so we can, I think, assume that these communities in Eastern Serbia, Bronze Age communities, were primarily engaged in copper production and not in metal production, not in alloy, not in production of finished objects. Yeah, and then of course we followed further the question where this copper ends, which was produced in Eastern Serbia, because obviously there are no local workshops for founding, and we did indeed find some using the lead isotope analysis, a number of objects, especially from the wider area of Central Balkans, which were produced using the copper from Eastern Serbia, Bronze Age copper. And it's particularly interesting because all these, at least until now, objects that we identified, where we identified the copper from Eastern Serbia, are very exclusive, singularly objects of, let's say, higher social status, these very impressive bracelets or armlets of type Juhor, and some other objects, but at the same time they are dating more or less in the same period as our sites. But at the same time, we also from this period found the first objects that clearly point at Trentino, at North Italy, as a source of copper for the objects produced in Balkans, and this will be the trend that will be then followed to the next centuries. Until the 9th century BC, we have a massive presence of Trentino copper all over the Balkans. So here you see the range of these objects where we tested copper from Eastern Serbia, and at the same time, this is the position of this one dagger that was obviously produced using the copper from Trentino area. So, we have started our investigations and already have some very interesting new results, but as I said, we have no signs of social stratification or wealth accumulation based on copper production. So this is something that I argue always with colleagues, because the copper deposits and copper exploitation is often called as a reason for the wealth of certain communities, and in our case it's definitely not the case. So we don't have any archaeological evidence of wealth or just social stratification based on copper. We have present of all groups. We have elaborated grave architecture, which is true, but no precious finds in graves. Of course, this could also be connected with the ritual background and the religious sphere. And from the 1600 onwards, we have a clear evidence of breakdown of seas of local copper production and seas of local cemeteries, because we don't have any C14 dates or other finds that could testify the continuation of these communities in Eastern Serbia. We will start now in the next phase of the project with strontium isotopes on cremation remains that could reveal some mobility patterns among interred. Thanks to Agne, I have to say, we did also the first chemical analysis on some bones or cremated bones from the urns. And although the sample was very limited, I sent only 4 samples from 4 graves. I noticed this very high value of mercury in one of the graves that could be somehow connected with the exposure to copper smelting and or vicinity of copper smelting activities. The one thing that is also left to be done is a reconstruction of environment and the impact of this widespread copper smelting that lasted over, let's say, 400 years in this area. And the question is if this somehow is visible in the environmental record. And we did find actually some animal bones for the first time in settlements, so we can make the first assessments of the subsistence strategies of these communities, since actually the soils in the area are not in the vicinity of the sites is not very favorable for the agriculture. So these are the questions that we will address and tackle in the very near future, but we will also, of course, continue with the field excavations in the hope that we will receive a new, fresh samples that will increase our knowledge. Thank you.
Thank you very much, Mario, Matthias. Thank you. Very interesting. Other questions? Someone? Congratulations, first of all, for getting funding for your work, which can be continued, and it's really nice to know. It's good to know that you have a lot of questions which you can answer in the future using different approaches. In this case, I think we have especially situation with cremated bones, where we work with specific material. And Mario, do you think it is? You showed some samples done now in the laboratory measuring the metal exposure in cremated bones. Do you see the perspective working with cremated bones within this framework of the metal toxicity?
I mean, the first attempt to show that is certainly try worth to try to see if, and this is from the methodological perspective also something that nobody has, to my knowledge, nobody has extensively did in the past. Of course, with strontium, there are some studies and results. Strontium isotopes, and in terms of mobility, can be applied on cremation remains, and this is very well done by Christoph Snock in Brussels. And I hope that we will get some new points.
I hope too. And Miliana has a question. Hello, Miliana. Nice to see you.
Thank you, Agne. Hi, Mario. It's really great. Great research. Congratulations on continuing funding. It's very well deserved. I'm obviously excited about all the data you're picking from the Balkans, and I'm wondering, just like, what would be your best pick for the Central Balkan metal production in the Bronze Age? Because you say that some of the Juhor stuff are coming from the Central Balkans and so on. Are there like known sites, or are there like deposits you are picking? Like, I know it's very much up in the air, but like, what's your best pick?
Yeah, but you mean in terms of production of finished objects, or?
of production, like the workshop, but also the
Yeah.
metal from the Central Balkans. Yeah.
Mm-hmm. Well, you know, from this period we have only few evidence of workshops. One is the Feldvar, which could, you know, in terms of chronology, could somehow overlap with Uhor type of bracelets. This is the one of the best known. Of course, we have some singular finds of casting molds, as you know, from everywhere, but a proper workshop, you know, it's still Feldvar is the only one, to my knowledge, from this period. If we just stay if we stay in the frame of Central Balkans, yeah.
Thank you. No, it's an exciting topic, and I wish you best of luck in continuing research.
Thank you.
And now I want to welcome our colleagues from Lithuania, Rimantas Vaisvalavičius and Virgilija Grigorauskienė, who will talk about patterns of change in chemical element levels in Lithuanian soils.
Hello, do you hear me? Do you hear me?
Yes.
Everything is okay. Now I'm going to share. Now should be okay. You have full screen our presentation. Yes.
Yes.
Agnia.
Yes. Perfect. Yes.
Okay. So first of all, we are two persons from different institutions, and I would say that with some different experience, because I'm more from agriculture sector, and Virgilia, my colleague, more from geography and also geology. And it was interesting that you invited us here to speak, and we thought what to tell you, and I decided together with my colleague to make a little bit some introduction about Lithuanian soils and heavy metals investigations in Lithuanian soils. Mostly it is connected with monitoring in the whole country in agricultural areas. So it's like agri-monitoring, also regional, geochemical, and urban territories mapping was done by our colleagues geologists. Some information was obtained about organic soils specifically because they, as you know, they can absorb a lot of different elements. Also, I would like to take this occasion to present one investigation we have done a couple of years ago, but it was modeling in investigation and quite interesting, still up to date, because nowadays we couldn't do such how to say complicated investigations due to the money, and finally some sentence about legislation of chemical elements in Lithuanian soils, and about the context of this event, as I tried to tell you that we are also fall a little bit outside this conference dedicated to bronze age metallurgy, because we are mostly dealing with our days contamination. It means with different sites that are left from previous, let's say, Soviet time, like abandoned military industrial site, that were contaminated with petroleum products, also with heavy metals, and many research was done on agricultural sites, because pesticides, fertilizers, and waste materials which are now pushed to used in agricultural lands, they may have potential effect of pollution for our soils. For instance, some fertilizers, they contain harmful elements in big amounts, like in phosphorus fertilizers. You may found some heavy metals, particularly cadmium, or in the pig breeding, copper compounds are used. So Lithuania is a small country, but our soils are very different. Our soil cover is really complicated. It is, as you see, a very different view, a lot of colors. It means different soils. We have, if some of you are, how to say, if you know some soil classification or something about soil systematics, so I would point that Lithuanian soils are divided into 12 major groups, 46 subgroups, 235 soil typological units. So systematics also complicated, but it is necessary to have in order to respond to this diversity of soil types. And soils in general are very young, more than 10,000 years. Only small part on the southeast Medininkai Heights, they have about 100,000 years. We think that it was before the last glaciation. Anyway, we have to understand this diversity, and our territory is divided in some soil regions, geographically, also representing this climate, micro topography, and other peculiarities. And here you see the profile. I hope you always, when you are as archaeologists are digging, you are going through soil profile. And the first layer, we call it A layer. It is humus or humus containing organic carbon. In Western countries, they used another expression. And then we have this mineral different layers, and this is sequences of layers, horizons we call them. And due to this sequence, we then are classifying soils to different groups. Like here, we have Lewis soils in this picture. So when pollutants or some materials, elements, if they come with air, or they fall from different aggregates, or if they are surrounded by just people or left somewhere, they are coming on the surface of the soil, and then the dissolution in the soil takes place, and some of them are precipitating or accumulating in the soil. Some are leaching, some are taken by microbial communities, some taken by plants. And here in this profile, you see that it is very common process in Lithuanian soils, leaching. So from the top layers, materials, elements are leaching to the deeper horizons. We call them B horizon. And here we can find in clay, in small size particles fraction, alurite. It is geological systematics. In soil science, we use expression clay. They are accumulating somewhere in the middle of the profile and deeper. So these investigations, they started not now, they started in 80s. For instance, Professor Vaichis in 1975. Then you can see here other names. I don't comment very much, but different investigations, scientific investigations were done in order to find how these heavy metals and other harmful elements are accumulated and acting in the soil profile. And later on was some big programs like integrated monitoring program, and it was used for monitoring of fixed agricultural sites, for agro-monitoring of prevailing soils in Lithuania. In that map that I showed at the beginning, I told you about these 12 major groups, and also monitoring of the use of diverse fertilization, various pesticide types and traits in long-term fixed trials, because in agriculture we still have some long-term trials. It means for 20, 30, 40 years in the same fields, in the same place, some treatments are continued to see these long-term effects. And it was done by Lithuanian Institute of Agriculture, and they had agrochemical research center. Now they call it agrochemical research laboratory, I think. And some data you can see on this figure. The study was quite huge. About 7,000 soil samples were analyzed in different soil regions and in different depths. Here you see only some elements like chromium, cadmium, lead, and other distribution in the upper layer, topsoil, from 0 to 20 centimeters, but also they have done from 20 to 40, from 40 to 60 centimeters, so also deeper layers were investigated. And it was found that mostly heavy metals are dependent on granulometric composition or texture. We may use another expression. It means particle size, also very important in this content accumulation is fine dispersive fraction. Myself, with my professor at that time was young PhD students, analyzed this fraction and also humus contents, pH, potassium contents, water loading, carbonate content, and other conditions. So most important, I would say, really is soil texture, because medium heavy textured soils contain more humus also, and in this top layer they can accumulate 2 times and more such heavy metals like chromium and nickel. Very similar data for copper, for zinc. So from the sand to heavy soils, to from sandy soils to clay soils, the difference is very natural, because mostly it represents natural amounts of heavy metals in the soils. The other stories with the peat and muck soils, they also can accumulate huge content, but I think mostly through the air, not from agriculture. Maybe, of course, some of them, some peat were used for agriculture, so some pollutants came also from agriculture. Also, they studied plants. So in Lithuania we have data about heavy metals amount in different plants, in different parts of the plants, like cabbages, carrots, red beets, onions, beans, green peas, and others. But we do not have, I think, any standards for that. But for soils, we have some standards, and it was found that no marked difference in heavy metals concentrations were found in vegetables and cereals and fruits grown in urban and in countryside soils. That shows for us that our soils are not generally polluted very much with heavy metals. The other story or other a picture would be in the cities, big cities. Here is from Kaunas city, this map. I'm sure something similar would be in Vilnius. Also, maybe there are some investigations done on some similar maps I could find, but I'm from Kaunas, so I used Kaunas city. So mainly concentration of pollution, contamination, or technogenic elements accumulation in the city centers, in the former industrial areas, because they were settled in the nowadays centers. Now they are moved to another places or changed to supermarkets, for instance. So some of the heavy metals they are accumulated in amounts that are above the permissive concentrations. Other long and huge work was done by geological survey. It was regional, geochemical, and urban territories mapping in Lithuania, and this is you see, all territory of Lithuania was divided into squares, 10 per 10 kilometers. Samples were taken from all these sites, and then was done different investigation of different element. So concentration of most microelements in Lithuanian soils depends on grain size. So it's very similar conclusion like was done by this agrochemical laboratory. Increases with the soil fineness, so it is the same tendency, the same trend. The largest values of lead and phosphorus accumulated in the peat soils, and the low clay loam soils best displays regional diversity of background values of most microelements. And the peaty soils for lead, phosphorus, and zinc. Also was some associations found that are some correlations like lithogenic, radioactive carbonate elements, clastogen, biogen, technogen. You see these elements sequences. Also, microelement association depends on the genesis of soil, parent material, and plant use. So everything is quite clear in this attitude, and what more I would have to say. Also they found that increased levels were in urban soils, particularly in the industrial zones. And here you see the data of my colleague Virgilia, that the upper layer of peaty soils, because as I told, some of peat soils were used and still are used in the agriculture, has several times higher levels of agrogenic lead, zinc, vanadium, chromium than the lower uncultivated peaty horizon. and some modeling experiment. We did experiment near the highways. We also took representative samples from the prevailing soil of Lithuania, from Lewis soil in different distances, near to the roadside, about 20 meters, and then about 350 meters. And we succeeded to take these soils like monoliths, like profiles. I mean, we took 1 meter undisturbed soil with all the horizons, and then we installed it into the laboratory, and we used to fill with some heavy metals. Of course, prior to start the modeling experiment, we made analysis about the content of these elements, and then into these 3 columns they were treated with a mixture of zinc, lead, and copper. And what is our results? You see, we find a huge amounts after a few months. So it shows the potential of soil to absorb, to accumulate of heavy metals. These are less or more natural, not exceeding permissible standards. And here you see these huge amounts, but still soil, I think, could accumulate even more, but we didn't have time because it was a project. We have to wait in the nature for many years, for 100 years sometimes, to see the final stage. And also we wanted to find if it is possible to remediate contaminated soil. So we even grow some plant, and even in this contaminated soil, plant can be grown. Of course, they are smaller, it is more difficult for them, but still plant are able to grow. And finally, about legislation, we have some standards that changing. In 2004 it was also for agricultural purposes, then it was in 2015 produced, but I didn't find the agricultural areas. It is from our health ministry this 2015, and for the environmental ministry they have environmental requirements for the management of chemically contaminated sites, and they classify all territories according to sensitivity to contamination to the 4 groups. It means highly sensitive to low sensitive areas, and agricultural falls into the 2nd group. It means sensitive areas. Then forest in group 3, and industrial sites in group 4, and that's why in these territories is allowed to find more chemical elements. Thank you for the attention, and if would be some questions, me and my colleague would be glad to try to answer.
Thank you very much, Montes and Vigilia. Other questions from the audience?
Any soil scientist in your group, in your are you familiar with soil science? I mean, are you soil scientist or you are more pure archaeologist or?
Oh, it's different, you know.
My question, what do you know about soil? Because it's also question, because many people, they don't imagine that soil are so diverse, so different, and even never have seen these profiles.
Yes,
They think
so
everything is.
it's a very important point what you speak about now. It's the soil differences and you know, structure of soils, and also the sensitivity of accumulation toxic metals into the soil. So I'm sure that Daniel there is probably an expert in this issue, but we also have to consider this working with archaeological material. Also, this variety of soil groups you showed at the beginning of the presentation, you know, Lithuania is a small country. How many regions we have with different soils, you know, it's also we have to think about it working also with archaeological regions and so on. So it's great what you did, what you showed now, and I'm really happy having you among us and bringing us new ideas to consider. But now I have to, Virgilia is writing some remarks concerning missing bronze age traces in Northern Europe. There has been tundra and taiga during that period. Due to geological conditions, thickness of glacial deposits is 20 to 200 meters. We don't have mining areas and metallurgy, only airborne traces on a distant ombotrophic peat box serving for construction of phytoenvironmental conditions. Mineralotrophic peatlands were drained during Soviet times and turned into arable fields. So thank you so much, Virgilia. It's also a good remark that, I mean, Lithuania is non-metallurgious. We don't have ores in copper and bronze age period, so it's a different situation what we had in what Daniel was presenting. So I mean, we have to collaborate with modern phytoenvironmental institutions, investigations of soils line in line to better understand the past, which is, I think, very important. So I think no questions are coming. Thank you once again so much. And now we switch to the medical part of our conference, and we are very looking forward to learn about toxicity now, about the toxicity nowadays, about heavy metals, clinical toxicology perspective. And welcome Linas Danavičius and Robertas Padaras.
Hello, thank you for having us here. I'm sorry for my English. it got rusty a bit. I'm living in Germany for 8 years, so it's when I'm getting stuck, will search for words. So I apologize for that. Okay, so I'll start with my presentation. Just a sec. Do you see it now?
Yes.
Okay, perfect. Okay, so I talk about heavy metals, what we are dealing with in the medical field, and I will try to put this topic in an archaeological perspective, maybe more to the point of archaeology. So we all talked about heavy metals, but what are they? What are the definition of these heavy metals? So if we look at the periodic elemental table, it's consists of mostly of metals. If you go a little bit deeper, we could see that there's heavy metals and metalloids there. There's lantanides and actinides. But actually, what define these heavy metals? Because when you search for a definition, you get a lot of answers, and a lot of these definitions from perspective of different fields of sciences. For instance, in metallurgy, they define heavy metals as heavy in weight. If from their density, for instance, osmium will be a really heavy metal. In physics, they define by atomic number, and sometimes heavy metals are defined even larger than sodium or even calcium. In chemistry, they define heavy metals by how do they form salts or hydroxides. In biochemistry, they define by redox reactions in water, how mostly the metals will give up their electrons and how easily they do that. In environmental science, they define heavy metals by their toxicity, or by their bioaccumulative properties and potential to pollute environment. So there are a lot of definitions. I found a very good diagram actually in Wikipedia, which they have like a 10 criteria, and physicists have an ideal gas. So ideal heavy metal would be the metal which ticks the most of these checkboxes, these criteria, defined by different fields of science. So mercury, lead would be the most heavy metal, so to say, from them all. From medical standpoint, heavy metals are actually the whole definition of heavy metal should be called toxic metal or toxic even elements, because some of these metals are not even metals. They're metalloids or metal-like substance, which does have some properties of metal, but not defined as a metal in physics or chemistry. So in medical point of view, these substances, these elements, which shouldn't be in organism at all, like xenobiotics, and they are disrupting the normal metabolic pathways, they are defined as heavy metals. Or sometimes even metals or microelements who are in organism and participate in metabolism, but in high dosages or by some different route of exposure, they considered as a toxic metal. For instance, zinc fumes or copper fumes. What defines heavy metals in medicine also that they are very difficult. The poisoning, especially chronic poisoning, are very difficult to diagnose, because they mimic every disease and every symptom possible, from bad mood to I don't know, brain damage and kidney damage and so on and so forth. Even there are comical cases, not a comical, but cases that bad children behavior or crime rate of children are associated with lead levels, especially with leaded gasoline levels in USA. There are some articles, old articles, considering that it could be association of that. So in this presentation, I will focus mostly on archaeological context, so bones, because we as a medical specialists have an advantage to deal with a living organism and make more research for them, because they have tissues and everything. And from an archaeological point of view, you mostly deal, as I understand, with remains, human remains, and that it's mostly bones. And I would talk mostly about chronic exposures, because acute toxicity sometimes leaves no trace on bones, or when there are no tissue left, you cannot say that there was any exposure. So in clinical context, in the medical field, we mostly deal with these elements. It's aluminum, antimony, arsenic, bismuth, cadmium, cesium, chromium, cobalt, copper, lead. But the cool kids in the block are these ones: aluminum, arsenic, cadmium, lead, and mercury. They are the most prevalent, and we have most cases of them, and we could just, I could talk more about them. So talking about bones, just to know the structure, so like there are 5 levels of structure, like organ, the whole bone, then the tissue elements, structural components, so the basic, the matrix, the carcass of the bone, which consists of collagen fibers and proteins, and hydroxyapatite crystals, which is a mineral part of the bone who gives strength. You can imagine bone as a block of concrete, of reinforced concrete with metal bars inside, which is like collagen fibers, and the whole concrete is the mineral part. And the bone is not a static structure. It's as we think about, just like a piece of minerals. No, it's not. Living bone, it's always remodeling itself. It's always, he has a circle of life, so-called bone remodeling cycle. It always destroys itself and recreates itself. When we grow, when the children grow, or the bone grows, the scales are tipped to creatine side, to the mineralization and tissue growth. And when we getting old, or there are some disturbances in metabolism, then the scales tips to the bone destruction side. And what heavy metals do, and I'm generalizing here, the ideal heavy metal should disrupt the metabolism of the bone, because it is similar to some microelements. For instance, valency of these heavy metals are similar to the calcium valency, like +2 or something like that, and they could disrupt the metabolism of the bone. So the disruption goes like this. Then the bone remodeling cycle is disrupted. Mostly it goes to the degenerative part, and bone loses its mineralization and gets brittle and degenerative. What are mechanism of actions? So mostly they inhibit osteoblast activity. Osteoblasts are the cells who regenerate or generate bone, and osteoclasts are the cells which destroys the bone and gives a signal to osteoblast to renew itself. But the heavy metals disrupts these signals, and osteoclasts wins in these cases, and bone gets a little bit more and more destroyed. So one of mechanism actually is impair of osteoblast and osteoclast balance. Another one is altered levels of microelements. And the very important thing that most of heavy metals damage kidneys, and chronic kidney damage leads to acidosis, chronic acidosis, and chronic acidosis leads to bone demineralization and degeneration. Why is that? Because bone participates in human pH system as a buffer. It's a third buffer, I think, the third important buffer system in organism for third level, and it gives calcium from the bones just to decrease H+ ions. Also, bone damage are actually damage to all organisms, but we are just focusing yet on the bones, are made from production of reactive oxygen species. These are the free radicals which damage the cell membranes and leads to apoptosis of the cells. And that leads to anemia, and that leads to stress erythropoiesis. That means the stress, the generation of new blood cells, and which could lead to swelling of the bone marrow, and also gives a pressure to the bone structure and could lead to degeneration of the bone. Also, it disrupts iron homeostasis and could some metals, some mechanisms of heavy metals could increase iron in organism in human body deposits, iron deposits, and some could lead to iron deficiency. But both these mechanisms could lead to bone damage. So yet again, these are the main heavy metals or toxic metals, and I will now go briefly on every of these most popular ones. So aluminium, it's the most abundant metal in the crust of the earth, found in many types of ores, have a single oxidation state, and it could get in our organism per os through gastrointestinal tract, in contaminated water or food. What is to know that in Lithuania we have an endemic zone which of increased aluminium, and if someone does the analysis, for instance, almost all analysis done in Lithuania of concentration of blood, aluminum concentration in blood, are sent to Germany, and they have a different norms because the normal values of aluminum in Germany are a little bit lower. And it could also a route of exposure could be inhalation when you expose aluminum vapor or fumes. What are the clinical manifestation? Aluminum mostly leads to anemia, then to encephalopathy. Most of the heavy elements, because they are disrupting the major metabolic pathways, leads to brain damage or neurological damage. So the symptoms, so it could be speech disturbances, neurological damages, dementia, and also aluminum is one of the prevalent, one of the most, one of the heavy elements which causes bone disorders, especially in children. The second popular one is lead. There are like two compounds of lead. There's an inorganic or elemental lead, and also there are organic lead compounds which are more toxic because they are soluble in lipids and could easily get to our organism through the natural barriers. And the bioavailability of organic lead compounds are very high. For instance, tetraethyl lead, which was used in gasoline to increase octane number of gasoline. It's very, very toxic. In even the vapors could lead to sudden acute toxicity. So how do we get lead intoxication? Or what are the routes of exposure of lead? So we get through the gastrointestinal tract, mostly through salts, lead salts, or organic compounds, inhalation, also organic compounds, and exposure through skin, only organic compounds because they are soluble in lipids. Clinical manifestations are mostly also gastrointestinal disturbances, central nervous system damage, and also could lead to kidney damage, and especially in children could lead to bone damage. There are typical lead lines in when we chronic intoxication of lead in children could lead to these lead lines, it's not an accumulation of elemental lead, it's just a hypercalcification because of a disturbed calcium metabolism. When we have mercury, the only metal which is liquid in room temperature, there are three main forms of it. Elemental is the liquid one without an oxidation. We call it quicksilver. Then there are inorganic salts. They mostly does caustic damage, like chemical burns. And organic, this is the most toxic ones because they could also, they are soluble in lipids and could very easily penetrate our natural defense systems like skin and gastrointestinal tract, could be absorbed very well and could go through the blood to the brain. And about elemental mercury, what could I say? That the fumes or the vapor are more toxic than then you ingest the elemental mercury, because ingested it's not very good absorbed in the gastrointestinal tract. The most intoxication of elemental mercury goes through inhalation. And clinical effects are also kidney damage, central nervous system damage, and also could lead to the bone damage. Then the heavy element that also damages bones most is cadmium. Root tox exposure are gastrointestinal. They don't have fumes, are or vapor very rarely, and organs that the heavy metal attacks is kidneys, lungs, gastrointestinal system, and bones. And cadmium could accumulate in bones as it has same valency as calcium. And last but not least, arsenic exists in various forms. Elemental, there's a gaseous form called arsine, organic form and inorganic forms. Arsenic metal considered non-poisonous due to its insolubility in water and bodily fluids. Very toxic is gaseous form, arsine. It was used as a chemical warfare, poison as a weapon. There are organic forms. This is actually one of the rare cases then that organic compounds are less toxic than salts or other forms of heavy metals, because mostly organic forms of heavy metals are more toxic than elemental forms. So acenobetaine and arsenic sugars are secreted by some marine animals as a byproduct of arsenic accumulation in these marine animals. But they are not so very toxic. And high dosage, actually, toxicity increases. So routes of exposure are also food and water contaminated. Also, we could get some arsenic from seafood, but as I mentioned, it's not so very toxic unless you eat a lot of it. Also, inhalation, they mentioned arsine gas and mucosal routes through the soluble in lipid compounds. What is very specific for arsenic, it's dermatitis. One of signs of the arsenic poisoning and actual thallium poisoning and other heavy metal poisoning are these called Mees lines, the lines on the nails. And the characteristic hemorrhagic vesicles of arsenical dermatitis are shown here. Arsenic are known that it causes the cancer and also have a lot of systemic effects, and also have makes damage to the bones. As I told, that there are a lot of definition of heavy metals. The best one is from maybe a musical science point of view. Heavy metal is a genre of rock music. So thank you for your attention, and maybe you have questions. I try to be brief because it's very, very broad topic, and I just try to just skim on the surface of it.
Thank you, Linas and Robertas. You did it perfectly well. Thank you so much for this overview. Now we are good oriented. What does it mean, heavy metals, and how it comes to the human body, and how dangerous it can be or hazardous. Do you have questions in the audience? Someone? Yeah, I don't see the. I think there are no questions, but I have a couple of questions to you. So I think it's also very important to consider the, you mentioned several times, especially children. So the categories of age groups, for example, how sensible they are to accumulate heavy metal poisoning. Children may be easier to be poisoned, let's say, or exposed than old people, when they elder people. So how is it?
Actually, when a lot of metabolism happens, there are a lot of reaction happens. There's a lot of stuff to disrupt for heavy metals. And especially when considering bone tissue, the bone tissue is growing, and there are taking place a lot of chemical reactions, and there's a possibility to accumulate there because it's growing, and there's a lot of taking place in this tissue during the growth.
So for us as archaeologists, it's also very important to think about, when we have bones to accept where we have huge acceptations. Yes. Mm-hmm.
Actually, a lot of poisons could affect growth and bone matrix and bone development in young years, during the growth years.
Mm-hmm. Thank you so much. And you probably know which bones are in which bones the bones heavy metals are mostly accumulated.
There's none like target tissue that it targets the most. Because they are xenobiotics, they don't have like a purpose there. They don't commit to the greater good for an organism. They just are there, and the more chemical reactions take place somewhere, the more they could accumulate there.
Mm-hmm.
Actually, I wanna
except for cadmium and some of them, but in most cases.
Robertus?
According to literature, it's quite strange, at least for me. But we find that the highest level of heavy metals was found in teeth and ribs. Ribs.
Mm-hmm.
Mm-hmm. It was very strange. I have no idea why. I have no idea, actually.
Mm-hmm. We have to ask our anthropologists or pathologists who are working with bones. Actually, they know the answer. So thank you so much. I see Laura Beirich is there. Laura, welcome. Thank you for connecting us from the United States. We're a little bit late, but I'm happy to see you. And it's very interesting to hear now about another topic, medical topic, let's say, about perspectives in the investigation of microbiomes and etc. So welcome, Laura. We are very looking forward to hear your presentation.
Thanks so much for having me. Can you hear me all right?
Yes, thank you.
Okay, great. So I'm going to talk a little bit today about how we might use paleomicrobiology to understand the effects of heavy metals in the body. I'll at the end, I'll throw in a couple little ways I think that we can tie this back to the environment and try to connect the dots between the two, and really use microbes as a proxy for all of this. So anyway, my lab is really interested in microorganisms. We're really interested in the application of using microbial genetics to understand the past, as well as take that and understand how to improve health in the future. So we do anything from ancient DNA of past human microbiomes to working with indigenous folks and industrialized people today on the health and how microbiomes contribute to health, and all the way through to developing microbial transplants for tomorrow, so to try to improve health. We also work on the ethics of this too, so I'm happy to talk about any of that, but I'll focus today in on the sort of microbiota work that we do in ancient humans. So for those of you who aren't interested in, or who may not know about the microbiota, but are interested in these sort of things, when I say microbiota, I refer to diverse communities of bacteria, viruses, fungi, parasites, protists that live inside and on the human body. So within the human body, there's estimated to be 100 trillion bacterial cells, which is a ridiculously huge amount of, of cells. And in fact, it's actually more than half of the total cells in the human body. And so we really aren't just human cells. We think of ourselves as human, but we're really hosts for these diverse microbial communities. There's over 1,000 species, which to me is really incredible. It's hard to think of 1,000 species of mammals. So then thinking about 1,000 species of bacteria, for example, is very difficult. And it weighs about 1.4 kilograms in your body. So it's about an organ's worth of weight, and has incredibly diverse functions associated with it. And those functions are linked to the genetic content in these microbes, which we call the microbiome. And so this outnumbers the DNA in our own human cells about 100 to 1. So if we estimate, for example, we have maybe 30,000 genes, and that's being very optimistic. Everybody has somewhere between 2 to 5 million bacterial genes. And so that means 99% of the DNA in the human body is microbial. And so if we're going to reconstruct how humans are adapting to their environments, how humans are responding to shifts, we really need to understand this other 99% of the sort of genome in the human body. It's important to me as well because this can also change and respond to our environmental settings, and things like heavy metals can be very strong selective factors on particular microbes that are doing well or not in the body. Now, maintaining these microbes is really critical for the human body because these microbes, for example, contribute to food digestion in our gut. And as a byproduct, they produce critical vitamins, things like vitamin B and vitamin K. Those aren't obtained from the diet. Those are obtained from microbes in your body producing them. They also metabolize drugs. And so these can be things that are purposely put into our body or not, but they also help train our immune system and prevent infectious disease. And last but not least, they can also aid in the detoxification of the body. And this has been much better studied, I would say, in animals rather than humans thus far. I think the best example I like to use is actually in that of koalas. So koala mothers, for example, feed their feces to their children or their offspring as a way of sort of dealing with the toxicity of eucalyptus and the eucalyptus oils in that plant. So these microbes are very critical for, sort of providing these basic human functions in the human body, including things like avoiding heavy metal toxicity. It's also really nice, though, because these microbes, at the same time they're doing all these functions, we can also use these microbes in the past as proxies to understand a lot more about what humans are doing, why they're doing it, and how they're responding. So, for example, because we know these microbes respond to different types of things that we eat, we know we can help reconstruct diets from this. We can understand more nutrition. We can look at natural medicines people might have been using, and we can understand more about immunity and infectious disease, as well as sort of chronic disease. And I'll talk a little bit about that in a second, and exposures to different environments, but also things like heavy metals. So many of you are probably going, well, how the heck do you do this? How do you investigate ancient human microbiota? And the short answer is that we use ancient DNA. And so ancient DNA just refers to DNA from any biological sample that wasn't intended to be preserved. And so most of you probably think about this in the context of bones, for example. But, broadly speaking, ancient DNA is really short, fragmented pieces of DNA. They're incredibly difficult to work with. Down here is a fragment length distribution of the pieces of DNA we work with. And this is a really common classic one that's used. And so the average fragment length is about 50 base pairs. I know in some Neanderthal microbiomes we worked with, we're dealing with about 38 base pairs. So really difficult to reconstruct. The sequences are also damaged. They're depurinated because of degradation over time. And so we get sometimes the wrong DNA sequence. We also know with microbial DNA, we can also get taphonomy. So some microbes may degrade at different rates because of their cell wall structure, for example. And so we know that we may get different recovery of different microbes. We also know we have to deal with mixtures of microorganisms. So we know, for example, from a human that's been buried in soil, we know that they may have mixtures of soil microbes and human-associated microbes. So we have to be very careful about how we decontaminate samples and how we address issues of contamination. So we've been spending, gosh, the last 10 years or so trying to, understand a lot of these issues, working with ancient DNA to reconstruct microbiomes. And so we've got lots of sort of more technical-based papers just on really dealing with many of these issues. But if we're going to reconstruct microbiomes in past people, we use two major sample types. One are coprolites. These can be really great at accessing microbes that were present in people's guts of the past. They're quite frustrating to work with, though, from a technical perspective, mostly because they're very integrated with ancient DNA or with ancient DNA from soils or sediments of wherever they were deposited. So we'll see big signals of that. We also know coprolites can continue to or the microbes present in coprolites can be quite different from what we see in a human gut. And so there's organic material in the feces when they're deposited. And so that microbial community can continue to feed on that organic material or can continue to respond to environmental context of wherever it's sitting. And that will sometimes change the sort of signatures that we get quite drastically. So that can be really frustrating to work with, but lucky for us, there is a different sample type, and that is calcified dental plaque, which is what we spend a lot of our time working on. And so this is a bacterial biofilm that grows and reproduces on the teeth in real time. So if you drink something sugary and you feel that sort of slime on your teeth, those are microorganisms growing and reproducing on your teeth. And if you don't have modern dentistry or you don't brush your teeth, what happens is that those will calcify from calcium ions in your saliva and form this rock hard cement-like matrix on your teeth. And you can see it here. You can imagine where somebody's gum line would have been, and then you can see the dental calculus sort of attached to the outside of the teeth. Now, today in modern medicine, it's usually removed when you do your annual checkups at the dentist or the hygienist. But in ancient folks, this would grow throughout the lifetime of the individual and provides us a record to go back in time and see what types of microorganisms the person had, but sometimes also dietary information or information associated with, how people, the behaviors in people's lives, for example, if they, have rope between their teeth or things like that. And it can also then provide, a capture for other things that are in the mouth. So things that would be present in saliva or things that would be moving through the mouth. You can imagine, for example, heavy metals in water or other things that people might be consuming might also be sort of caught within this matrix. And so we've been spending since 2013 really figuring out ways to reconstruct this. And we published the first study on this in Nature Genetics in 2013. We're able to sort of show that microorganisms are incredibly well preserved in this matrix. And so this is a scanning electron microscopy image done by Keith Dobney, really showing the cocci of the individual microbes present. And if we zoom out a little bit, we can actually see the calculus forming throughout someone's life, almost like tree rings, sort of these rings on the surface moving from the tooth to the outer surface. There's lots of folks doing this research now, and it's really exciting to see where it's going to take us. And I think this is quite different from maybe what many of you may be familiar with, which is a lot more of the sort of pathogen genomics work in ancient DNA or in that. Now, ancient pathogen genomics can also still tell us an incredible amount about heavy metal, exposure and what pathogens are circulating in these areas. And typically, we get a lot of that from bone. Much of it's obtained from the tooth pulp, which is where there's access to blood. If somebody died from a systemic infection, for example. But there's also people looking to get pathogens from soil, particularly, for example, the pelvic region of a body where someone may have been buried. And there's other people working on pathogens associated with, say, for example, feathers or hair or even eggshells. But there's been a wide range of pathogens that have been described using ancient DNA. The list grows every day. This is just the list that we published in a review a couple years ago. But really, like it's an incredible resource to reconstruct individual microbes as well as these entire microbial communities. So to give you an example of what we might use this dental calculus data for, I'm going to tell you a little bit about a paper that's coming out next month in Nature Microbiology, where we reconstructed ancient British calculus through time and really tried to understand why it was changing and how that might be linked to health over time. Because I think this is something that you could apply in many locations, including in the context of metallurgy. And so what we've done here is look at 235 ancient oral microbiomes spanning the last really 2,200 years in Britain. And this includes 127 well-contextualized individuals from London. And so we have all sorts of information about paleopathology, all sorts of bioarchaeology on these folks. And it really allows us to tie the oral microbiome to signs of systemic disease and of health in these populations. And a lot of this work was done by Abby Gans and Andrew Farrer, who were in my teams at both University of Adelaide and now here at Penn State. One of the big things that we found that's, it's a very technical observation, but it really changes the way that we do oral microbiome research. And that is to understand that we also have different types of oral microbiomes depending on where we're sampling in the mouth. For example, if we're collecting dental calculus. And so we also see, for example, that there are differences in microbial communities collected from incisors, shown here in yellow, compared to molars, shown over here in green. We also see differences in microbial community linked to the size of the dental calculus, as well as which surface of the tooth the dental calculus was sampled from. So it's incredibly important when we're collecting samples for ancient microbiome analysis that we really are maintaining the metadata or the information on where that calculus was sampled, that we're not mixing calculus from different teeth across the mouth, which is something that, for example, is being done a lot at the Max Planck in Leipzig, which is incredibly problematic because it destroys a lot of these signatures that we're seeing. And it's also really important that we sort of get controls to be able to compare this and really understand what's going on in an individual population. But once you do this, what you can start to do is reconstruct the microbial communities that would have been present in people of the past. And in England, for example, we see that a lot of people have these microbial communities shown here in green, which are dominated by a microbe called Streptococcus, or dominated by microbes in the genera, in the genus Streptococcus. Whereas we have whole other microbial communities that are dominated by an archaea, Methanobrevibacter. And this is mostly Methanobrevibacter oralis. And this microbial community shown here in pink doesn't really exist anymore in industrialized humans, so we think it's largely gone extinct. But that really matters if we're trying to reconstruct what types of microbes people had and then understand how these microbes might be responding to environmental contexts. We need to get these reconstructions correct, and we need to understand what the sort of baseline is, even without exposure to metals. So anyway, even in England, we sort of have these extinct microbial communities that don't really exist much in modern populations today. But we really wanted to understand what was deriving the presence of these two microbial communities, and what was going through this. And we used a lot of that beautiful bioarc data from London to test much of this. And it turns out the only thing that really explains the shift from these two microbial communities is the arrival of the second plague pandemic. So when Yersinia pestis, or the Black Death, as you may have heard it called, arrives into London and upwards of 30% of the population pass away, we see this sort of shift in the microbiome, moving away from the Methanobrevibacter communities, although Streptococcus communities are still present before then, but really pushing into more being dominated by the Streptococcus communities that we see today in modern populations. And we think this is really interesting. It could be associated, for example, immune selection in these people, but we think it's actually much more complicated than that. And one of the things we've done to really show why this might be more complicated is to look at microbial functions. Now, for response to metallurgy, I think looking at microbial functions, or what the microbes are capable of from a functional perspective, is going to be really, really critical in understanding how people are responding to metals and how they might be sort of using microbes to detoxify their bodies. In this case, we're using functions to look at diet and really understand, broadly speaking, what microbial functions are in the mouths that might be associated with the foods that these types of microbes are exposed to. That old adage of you are what you eat is also true for your microbes. Your microbes are also eating what you're eating. And so that will sort of carry on together. And we do see that the Methanobrevibacter community, that one that sort of is lost through time, has fewer genes associated with meat and dairy and sugar consumption. And that really this microbiome that's Streptococcus dominated really has more of those genes, which is akin to more of an industrialized diet. And this really matches with what we see after the arrival of the second plague pandemic, where there's fewer people to work. And so people are able to demand higher wages and also get much easier access to things like meat and sugar in their diets. And so this really, it matches on with the sort of cultural and the sort of social changes that are happening in society at that time. So we can see biological impacts of social cultural change, which I think is really critical and really important for our understanding of how the past influences our health. We're also able in this population to understand how these microorganisms may contribute to systemic disease and not just oral disease. So I think when people think of an oral microbiome and dental calculus, we're really just thinking about how oral microbes are linked to things like dental caries or periodontal disease. We're not necessarily thinking to how they're related to the rest of the body, even though we know in modern populations they are associated. And so again, using that beautiful bioarc data from London, we're able to show that certain microbial communities are linked to things like periostitis, osteophytic lipping, and porosity in the skeleton. And that really can be indicative of, again, these sort of immune states that are associated with particular microbes in the body that may be stimulating more inflammation. And that may then have sort of impacts, not just in the mouth, but also holistically. So we'd be really excited for example, to compare the presence of different functions that are linked to, for example, metal resistance or the ability of microbes to deal with heavy metals in their systems, and then correlate this to, for example, the presence of systemic disease or oral disease as one type of example. Now, there's lots of other things you can do with dental calculus. That's just the beginning, especially when it comes to looking at heavy metals. One would be to track the individual evolutionary history of microorganisms. And I think it's important to realize that we can do this not just in pathogens, but also in these commensal microbes, the microbes that are present in people, every day, and in populations over thousands and thousands of years. And so this is one example of that. This, again, is this archaea, Methanobacter oralis. Here we were able to reconstruct it from a wide range of ancient humans as well as Neanderthals, and we're able to track it through time. In this paper that we published in Nature in 2017, we can actually see that Methanobacter is transferred somehow. How is still we're uncertain, but somehow is transferred between Neanderthals and humans about 120,000 years ago. And so tracking where these microorganisms are coming from and what adaptations they may have from whatever hominid they're coming from, or whatever culture or group of population of people they're coming from, is going to be really important in understanding how people are adapting to new environments, and how people might be interbreeding or mixing with other human cultures to sort of provide that adaptation. There was also, this just really pushes into showing you that we can really do reconstructions of these genes that are associated with both heavy metal resistance and antimicrobial resistance. So for those of you who may not be familiar with sort of more microbiology associated issues, we know that many of the genes associated with heavy metal resistance are also directly associated to antimicrobial resistance, or AMR. And so there's been studies showing that both the same gene families, they're mostly transporter pumps that sort of take heavy metals and pump them out of the cell wall structure, really can do the same with sort of some antibiotics. And so these are really interesting in my mind, because we can understand the history of how exposure to heavy metals may have influenced the modern adaptation to antimicrobial resistance. And we can, again, do these in microbes that are present in the human body all the time. That can be a sink for pathogens or a sink for infectious disease. And it's really, really great. So this is an awesome paper done by Brealey et al. In Current Biology in 2021, which is not from my team, but they did this from bear dental calculus, and we're able to show an increase in AMR genes over time. But many of these genes are linked to heavy metal resistance. And so if you can even see it in bears, I'm I'm very excited to see what we'll see in humans. And that work is sort of still ongoing. And last but not least, I think it's also really important to think about these functions, not just within the human body, but also within the soils and sediments that we may be looking at humans from, because this will really provide a comparison to what's in the environment, as well as what's in the calculus and what's in the human body. And so this is work done by Vilma Perez, who's at the University of Adelaide, who was a postdoc for me many years ago. But she's been doing a lot of work now looking at microbial communities present in sediments, and then turning around and looking at them and including their functions as proxies to understand how microbial communities are changing and why they're changing. So for example, if we think metallurgy begins at a particular location at a certain time, we could use microbes to say, do we see microorganisms adapting to an increase in heavy metals? And do we what functions do we see present in those microorganisms? And then can we track those same microbes and functions into humans if they're sort of working in that location? And what does that mean for their health? I think that's really the overall arc that would be really cool to do in this type of research. So with that, I'll just leave you with some concluding remarks, mostly that ancient microbiome research is incredibly technical and requires a very detailed and thoughtful approach. But I think ancient microbiome research can really reveal a lot about past people, but also their health, diet, and exposures, including that from heavy metals. So with that, thanks so much for listening. And if anybody has any questions, I would love to hear them. Thanks very much.
Thank you very much, Laura, for your presentation. It's just amazing what is now possible to do with the human, let's say, calculus, dental calculus, and how important it is to our questions as well. So, other questions to Laura from the audience, please? So I have one. We are going to select 500, around 500 teeth. Is it enough for such analysis? How big should be the databases for analyzing microbiomes with regard to, let's say, first resistance to metal, to heavy metal exposure, or also to the diseases connected to metal exposure? So how big should be the database, and are these samples, must they be destroyed? My practical question.
Yeah, so all of the work that we're doing is destructive, meaning that we need to remove dental calculus from a tooth. All of that said, all of the work that I've shown today is from one side of one tooth from each individual. So it's really what we would call minimally destructive, because it leaves the rest of the calculus in the mouth. So for example, you could retrieve calculus from the inside of one back molar and do the analysis that I was talking about today. So you don't need to remove all the calculus from all the teeth. Don't let anybody sort of go in and do that and destroy collections. So really it's a small amount that we need. And our rule of thumb is that if you can pick it up with tweezers, it's big enough to sort of work on. So that's a good thing. But I would say in regards to the 500 number, that's excellent. So most of the studies that have been published to date have been done on handfuls of individuals, 10 or 20 people. And it's really just not enough folks to be able to do some of these comparisons to systemic disease. It's also not big enough to understand how the microbiome varies over a population. And we know that we have population differences across Europe and through time. And so it's really important to sort of be able to survey broadly enough across the population to really then understand that. What we'll have to be thinking about, though, is controlling for things like age that we know should associate with the microbiome, trying to control for different geographies, like how many people do we have from an individual site, and can we maximize individual sites to sort of minimize geographic variation. There'll be all sorts of selection within that 500 that we need to be smart about and think about, but 500 is enough, and I would say even sort of 300 would be enough to really start looking at that. And that's important, right? Because maybe 500 teeth doesn't mean 500 calculus samples. Maybe it only needs 300 calculus samples if someone's already sampled it. And I think, it's also important to be thinking about the fact that many calculus samples only come from adults, right? We often don't see it in children unless children are quite sick with something. And so really we're kind of limited in who we can sample from. Does that make sense?
It makes, thank you. So I mean, for analysis, we are dealing with the adult people mostly, yes. So I mean, you already mentioned like the accumulation of microbiomes, the huge amount is mostly in the adult teeth, not in the children yet, because they are children. They still live a short period of life, and adults, they do have a lot of experience, and also it remains in their bodies and in the teeth as well. Interesting is another question. Can you guess, for example, how many generations people need to develop kind of resistance to specific kinds of diseases which can be caused by heavy metal exposure or toxicity? So how long should this period be? I mean, you mentioned many aspects, diet, kind of, we have also detox products which can, make a metabolism quickly and make boundaries for accumulating heavy metals in human bodies. However, when we speak about the genes, how many generations can we expect? 2, 3, or how long it takes for developing specific kind of resistance?
Yeah, I mean, that's a really great question.
Yeah.
We have a little bit of preliminary work where we've done ionomics in calculus to look for the presence of heavy metals. And I thought about showing that today, but it's very preliminary, and so I don't want to send people on a wild goose chase that's wrong. But at least in that, we can see it change rather rapidly. So we know, for example, heavy metals are really present in folks from the Industrial Revolution and much less present in the generations just before the Industrial Revolution. But that's a huge change, in environment. And so we, we've looked at one of the biggest changes, and obviously we see sort of a difference in heavy metals. But and so that for us, is sort of one generation or the next generation, right? And we would assume many of these microbial adaptations would be very quick. Microbes are incredibly good at horizontally transferring genetic information, right, using plasmids and things like this, especially people that are more out in the environment and exposed to environmental settings. We would sort of expect to see that. Heavy metals are incredibly toxic to microbes, just like they are to humans. And so there's a really strong selective factor for microbes picking up these genes and figuring out how to use them very quickly, because if not, they're killed off, right? And so really, from a microbial perspective, it's very rapid, and would happen, inside individuals who are directly exposed to whatever that is. I do see there's a couple of questions in the chat, and somebody's actually asking, would it be useful to compare this in modern people who work with metals? And absolutely, I think that would be a great idea, right? To sort of do an experimental biology type study, in folks who are doing metallurgy today. I think we'd also have to think about how different the practices are in folks working today versus in the past. But, I suspect people who are individually exposed to that day in and day out, right, sort of doing these sort of activities, those are the folks you're going to see these sort of largest spikes in and the largest sort of changes in, even in that single generation, that single sort of person who's exposed to those things, because these microbes have, again, a really strong selective factor on them.
Thank you so much. And also, Irida Tomasic is asking to see on the chat, considering the soil can be contaminated with heavy metals, past or modern, in which the individuals are buried, how prone would dental calculus be to processes like diagenesis?
Yeah, that's a really great question, and nobody's looked at that directly. One of the saving graces of calculus, though, is that many of the microbes that get caught in dental calculus, we think actually probably die during the life of the individual, because they are sort of, they're locked into this calcium, cement-like matrix. And so what you would expect to see, or what I would expect to see, would be that we would see soil microbes that are not typically found in the mouth, because we know many mouth-specific microbes would probably have these sort of signatures of adaptation to heavy metals, whereas microbes that we know are specific to the oral cavity, for example, should not, if somebody was buried in that and the signatures came along later and the soils or sediments being contaminated with heavy metals for some reason or another. So having those controls from the sediment and the soil directly associated with an individual is going to be really critical, and I think really important to try to figure out some of those potential post mortem interactions, right, that we might sort of see. But yeah, it's probably something that we're going to have to test and look at directly, I would say, in these studies. But I don't think, from everything we're seeing so far, we can usually get a pretty good split between the environment and what's in the mouth, if we've got good controls. So I think we'd be able to sort of sort that out.
Thank you. I mean, the same problem we do have if we measure the heavy metal exposure levels in the human bones, which it's the same question about diagenesis and how exact we are, or maybe we are wrong, because all these amounts of values we measure could derive from the diagenesis, from the contamination in modern times, etc., etc. So here is a huge challenge, working with this material and to divide and we have to be also careful here in this case. But you are optimistic, which is good.
Yeah, I am, mostly because if those microbes have died, you know what I mean, and were dead before the person sort of is there, it's going to be difficult for them to uptake, for example, heavy metal resistance genes.
Yeah.
We might still see heavy metals present in the calculus, but that may be different from the functional profiles of those microbes. So I think that's how we can sort of tease it out. But it'd be great, again, to do some modern sort of experimental biology, right, and take teeth with calculus and bury them in contaminated soils versus non-contaminated soils and see what happens, you know, to the calculus, for example. So yeah, it's a great question for sure, and something we're going to have to watch out for.
Thank you. So now we should have a presentation of our colleague Miriam Nivultova-Fishikova, but unfortunately she's sick and in the hospital. So I say hello to her from all of us. She wanted to speak about bioarchaeological analysis of bones for the detection of pathology. But we already mentioned many of aspects of this topic, and I mean, it's better that she is not here, but I hope for future meetings too, when we can hear about results, concrete results. But the main question, what Miriam is doing in recent research, if we are talking about heavy metals, she is going to measure the contamination levels in specific bones of human bodies. As we already heard, they are ribs and of course teeth, and to measure it, to have values and to judge how the body was poisoned by the heavy metals. Those bodies are from the settlements and especially from burial sites from the vicinity of prehistoric minings, which these societies living there had direct contact with the metals, with metal exposure. And so this is a very interesting approach, what she tries to do. And furthermore, she will try to recognize pathologies on bones. We already heard in the presentation of Linas and Robertus about the effects of heavy metals to human body. So many of these hazardous effects are visible on bones physically, you know, like osteoporosis or other kinds of diseases. And Miriam is ready to recognize this on the human bones. So in close, for example, in the burial sites where we know it's a close community buried, and like Nizhna Mishla, for example, or other burial sites, and she can recognize specific pathologies. Of course, it is hard to say, okay, osteoporosis, maybe the reasons are different and not exactly the heavy metal, but if we have teeth, we can combine, for example, that Laura is already doing. So take teeth, do the microbiomes, analyze the metal combustion in the teeth and also in the human bones from the same individual. And what is interesting that in the burial sites, we can also divide societies in the groups, kind of age or sex. And then we can combine the results. Do we have specific groups? For example, maybe there are men who have a huge amount of heavy metals in their bones and other not. And we are all living in the same place, kind of in the same area, not huge, you know. So we can maybe divide specific groups of society which are more in contact with heavy metals and others are not. So maybe we can also speak about social stratification among those people. So and Miriam's idea is to work with all these questions. And it's of course said she cannot explain more now, and I am not a specialist in all the methods used for the investigation, but it has a great potential, I think. And I think we can, having such a solid base of anthropological material in the area of investigation, we can have wonderful results in the future. So that is it's a good perspective, a good perspective for our work. Yes. So okay, I think yes, we are now. Yeah. We're now on time for the discussions, and I'm really happy having such a successful day, but with very, very interesting presentations connecting different aspects, which are all connected to the heavy metals. And I want to open the discussion, maybe some comments or generalizing ideas. What have we done today? So what do you think about this heavy metal pollution, heavy metal exposure, environmental issues, and how humans could react to all this, human organisms? Can they follow this? Or is it an utopic task? Someone has a comment? No? So, okay. I will try to go through to summarize our work today. So we have different aspects, of course, to discuss. And first, we have to deal with the anthropogenic factors and human activity with metallurgy, which really increase, as we saw today, increase the pollution in the environment. And the main question is this polluted environment dangerous for people living there in these places? Can we expect the exposure from the soils, from the environment to human organisms directly in the Copper and Bronze Age? We know we heard today the presentations of today's situation in Lithuania, for example, the variability of heavy metal pollution in the soils and reasons why the heavy metal are in the soils, etc. We also heard about the modern medical science and the impact of heavy metals, but how huge should be the values in the prehistoric times, but in Copper and Bronze Age particular now, to judge about toxicity. This is a question. How can we find the values and how can we compare these values with really hazardous values today? So I think this is one of the questions to consider, but I am strongly convinced that this is an important question for archaeological science to investigate and to consider the aspects of, let's say, dark side of metallurgy, what metallurgy did actually to people. And I think that we can also consider that specific group of society was more involved, of course, to metallurgical activities. And this group was also different. Maybe some of people were miners who were sitting in the mines and, you know, bringing copper to the daily light, and others are those who are working with these ores, and they have vapors. And we remember our discussion today, what Paolo actually said about the vapors and processing of ores, and also different chemical compositions of ores. All of those ores have some specific amount of metals which through the smelting can come into the vapors, but not all the society got these vapors, only part of this. But anyway, it's also important thing, and maybe we can find those individuals in the burial sites or in the settlements like Santana. What we remember today, there are graves within the settlements. In the settlements where it was active metallurgical activity. So maybe we can recognize specific people who are more affected. But we also have to think about the societies, all the communities, and how they live, what they have eaten. We haven't discussed today the diet. We haven't discussed the food chain, water contamination, for example, or also pottery made of clay, and clay is very, very flexible to absorb heavy metals. So we did not discuss it, but it's also one of the points, how the environment, polluted environment, affected the food chain. I already mentioned in my introductional part today. What have people eaten? These bones, animal bones, or fish bones, or what have they, which water they drank, for example, etc. So these are questions which are, of course, with risks, but very important, I think, and we have to consider it also in the future. The good thing is also what I can say when I think about today's presentation, that we have a long period of metallurgy. It's a copper and bronze age. So we can compare different phases of metallurgical activities. And we also saw peaks in some presentations, peaks and downfalls of specific activities, metallurgical activities. And all these phases are also important to think about heavy metal exposures and heavy metal impact to humans, to nature and humans also. Yes, different techniques applied for metallurgical activities is also important. It's kind of also, I mean, natural circumstances, different ores in different regions, but people, they selected the ores and they applied different techniques for working with these ores, and this is also interesting. And what it's also interesting is behavior. I mean, now if we speak about people, about the societies, interesting how they deal with metals and where they live, settlements. We saw fantastic examples, but fortifications, for example, kind of isolation, etc. But we also saw sites which are not isolated, not fortified, or without any any evidence for being fortified or so it's also interesting. And yeah, the social status I already mentioned. We have specific regions where we can, in my opinion, speak about kind of no elites or no expressed elites. We cannot see it on archaeological material. And I remember the presentation of Maria with cremated burials without any exceptional grave goods. So the societies did not wanted to express some social statuses, but these societies live in an environment full of metallurgical activities, and it's good that we can start to work with cremated bones in order to recognize the question mobility of people or other things like it's a huge perspective working with cremated bones to go further into this question of social positions and of behavior during metallurgical activities, but also to use cremated bones for our questions like metal exposure. What else, colleagues? Please make your notes. What else? Yes, there are really many aspects, and I think our conference is a first step in the future investigation about heavy metal exposure and its impact to environment and human health. And we can open the door for new insights of recognizing of past societies, their behavior, their interrelationship with metallurgy and with metal, with products, etc., and to maybe to discover new points of rethinking. What does it mean? What does it mean to live in the areas, in the mining areas? How people lived it? How was the condition of their life and health? What did they eat? How old were the most damaged people by toxic metals? And most important, how we deal with this toxicity, if they know about it or not, maybe they did not at all, or maybe they knew that and tried to do something against this toxicity, because metallurgy is a long period and people did not stop to use metal, They used the metal, they produced massive metal, but they also deposited the metal artifacts to the environment. They left massive hoards, etc. So it's very interesting aspects to think about this, and especially if we have this opportunity to work with modern methods like microbiomes and genes, and to see how people managed to, or how they developed resilience to heavy metals. So I think it's a very interesting topic, and I hope it is not the last meeting. I hope we will work together. And yes, thank you very much for everyone who was attending, who was listening. This conference was recorded, and please, if someone does not want to share the presentation with the rest of the audience, write me an email. But yes, I think it was very successful and it was great pleasure to work with you. Thank you very much. Yes, no comments at all. Okay.
We're silent people.
my English, but you know.
Oh, you're perfect. We are silent.
I am a kind of person who do not hesitate. So
thank you, Agnes, very much. It was a great day today with all of you, and I learned a lot of things. And it's fantastic to see all those broken pieces. And it will be great if someday we will get the opportunity to collect all them and make the whole picture. That will be perfect.
That would be perfect. Yes. Thank you for your support. Yes, nice for everything. Okay, Bianca, hey, I see you too. Nice. Okay, I disconnect now. Have a nice afternoon. Evening. We have already dark here in Lithuania, you know. It's a night already. And I will contact all of you. I will send the material of the conference and it will be, you know, it will be accessible to repeat what we have done today. Okay. Okay, goodbye, my dear colleagues. Bye.
Bye.
Bye.